Well, namaste. Good morning, everyone. We welcome you all to our third training program on high performance fibers, application and testing. It is a privilege to have you all join us today, both in person and virtually. We are delighted to host such a diverse group of gathering, our speaker, distinguished guest, and enthusiastic attendee. Today, we will engage in interactive sessions such as on high performance fibers, dyeing and finishing, defense applications, and physical properties of fibers. So the sessions will result in knowledgeable discussion, innovative ideas that chart new paths in this particular area. Thank you for being here and contributing to this dynamic and inclusive event. Let's make this event an inspiring and enriching experience for all. Once again, we welcome you all. We will start our program by offering prayer to the goddess of knowledge and wisdom, Ma Saraswati. Now, on behalf of ITT, I would like to invite you all to join the Saraswati Vandana. Thank you all for joining. Now, it is our privilege to invite our director, Dr. Nandan Kumar, to welcome our guest and to brief the session.
Thank you, Shwam. Good morning, everyone. We have an interesting event today, and very briefly, I would like to say why we are doing it. The idea is very simple. We really want to share these basic knowledge to students, to researchers, and even to companies who are willing to invest in this area. And I'd like to thank Pushpinder sir, who is going to talk on the definition of aramid. We have Professor Ghosh, who is going to talk about properties of physical properties of fiber. Then we have Manorma ma'am, who is going to tell us about defense requirements. And these are the online session. After that, post lunch, we'll discuss various case study, and we'll have demonstration session in our lab. So let's start this with a note. We are at the end of 2024, and we look forward for many more sessions in 2025 with loads of consultants and various experts. With this, thank you so much.
So, our first speaker is Dr. Nandan Kumar sir. So he has over 17 years of experience in the field of protective textile. He did his bachelor's in textile technology from the NIT Jalandhar, followed by his master's and PhD from University of Leeds, UK. He is director of HPT and ITT. He is interested in R&D and published several research papers in reputed journals and conferences. So now the floor is yours.
Thank you, Shubham. I'm just sharing my screen. Like I said, we have very interesting lectures lined up. So the plan is I will introduce these fibers, and then again I will come back to uh, my presentation after Manorama ma'am's lecture, so that we can discuss all the fibers in detail. And so yes, high performance fibers. We all know this has already touched us in one way or another. Um, we are using variety of fibers which are now can be characterized either as high performance fibers or high performance textiles. So the best example I keep saying, we have 95 or 96% cotton and hardly 4% of anti-static fiber. That is making the whole textile anti-static. Or now it's going towards being used as a sensors or smart textiles. So, like I said, this is the time we need to invest our time and effort on understanding, talking to like-minded people. Very briefly, because I can see we have a lot of students here and uh, business owners who are not from textile backgrounds. In just 2 or 3 slides, I have tried to explain why we should be looking towards this and why it's going to be very important in next 5, 10, 15 years. Obviously, the basic requirement is lightweight. We want our products to be lightweight. We want it to be durable. We want it to be multifunctional. A very simple example. Wait, just let me see what's happening. Shubham, can you just share from here? Can share. This is WhatsApp. Yeah. Yes, apologies for that. So yeah, what we are trying to do, we are trying to understand how we can develop a product which is lighter in weight, which is durable, and which is multifunctional. At the same time, how we can use some of these materials which are very costly. This is the best example. If you can see what I'm holding a spool of tungsten wire. Now this is 20 micron tungsten wire. This will cost you 12,000 rupees a kg. Now imagine I have to make 1 ton of yarn, which is having this tungsten wire inside it. So now the challenge is, it's not only about securing the order, but also what are the challenges? When you are buying tungsten wire, how you are going to test it, whether your material is reliable or not. So these are the challenges we are going to address in this lecture. And the idea is just to inspire each other so that we can discuss, we can talk. And obviously, we all are doing a lot of confidential projects, but a part of projects we can share with each other. That's the idea. And once again, these fibers are becoming very interesting because now we are talking about extreme conditions. There was a time when we can trust on test results which are done at room temperature. Now we need to ask whether the testing was performed at higher temperature, or can we guarantee that the results we will get at -20 or plus 100 degrees centigrade. So it's not only about using these fibers, but also how we can test it correctly and how we can make sure that our testings are as per the international standard. Okay. So what we are doing, and one side we are designing product, other side we are working on improving our testing standards, improving our testing method, how we can do this testing at extreme condition. A very good example is cut performance. We have seen that the cut performance, which is coming at room temperature, goes down if the temperature goes up by 50 or 60 degrees. So same is the case with thermal conductivity. Thermal conductivity data at room temperature changes when you do thermal conductivity at 100 degree or 200 or 300 degree. So it's about questioning the product as well as how we can change the testing. So this slide is very important for researchers who are looking for areas where they should be focusing on. So future is all about testing or developing product for extreme conditions. Blending techniques is going to be very interesting in future. We are doing a lot of fiber blending, then we have a yarn blending, then we have a fabric blending. We'll show a lot of case studies. A core sheet structure, this was interesting before. Now again, it's picking up, and we can see a lot of designs of yarns or textiles where inorganic fibers are hidden inside, and we have organic fibers next to skin. Recycled with virgin, I can tell you this is going to be the next 5-10 years, huge business. We can see how you can blend recycled high performance with a part of virgin and how you can make it good quality products. Treated with inherent, Kushwinder sir will cover this area in the next slide. And the most important, which is my favorite, blending natural fibers with these materials. The best example, we are doing a lot of work on brown cotton. We'll show you some case study also, how we are using brown cotton, which is genetically grown in brown color, how we are blending that with high performance materials. And the idea is to develop some commercial projects. Again, this slide will be interesting for business owners who are having manufacturing setup. So in this slide, I'm just trying to show that a simple case study, open-end plant in Italy and in India, where same monthly 10 tons production with a team of 13 to 14 people, but the turnover for Italian plant is 100,000 euro to 150,000 euro every month, where in India we are 15,000 to 25,000. So what is the difference? The difference is the selection of your raw material. So I'm not against processing polyester, cotton, wool. It's fantastic. We should do it. But we should look into how we can use some of these materials to develop some high value product. So that, with the same machine, same manpower, same team, you can achieve higher turnover. And with higher turnover, you have additional benefit. That is something can be done even by small companies or even by big companies, And most important, because we are manufacturers, we have to manufacture to survive. And for us, the price of raw material is very important. And you can see the price variation. You have certain fibers which are coming from $45 to $60 to up to $8 to $10. This is another reason why we should be learning about this fiber, or why we should be talking about this fiber to each other. The two simple case studies I have shown here. We bought 1 ton of black pararamid, 500 kg of black pararamid. We have bought this black pararamid from 3 suppliers, and only one supplier fibers were good. Rest 2 was having problem. And I can tell you from my experience, sometimes it's very difficult to prove that there is a problem in fiber, you know, because most of the time they will blame your carding machine, draw frame, speed frame, ring frame, ligament speed, cylinder speed, they will say fibers are getting ruptured. But to prove that the problem is in fiber so that you can get your money back, if something can only happen when we share this knowledge and when we can discuss with each other, we inspire researchers to work on this field, try these materials, develop samples. So I think first few slides, I was trying to just showcase why this is important so that, we can spend more time. In 30, 40 minutes, I'm going to touch base many fibers. And definitely in future, we have to give at least 10, 15 hours on each fiber. The area is so vast. We are working on developing a module, 15 hours lecture just for aramid. This is that big area. So introduction, we all know high performance fibers, at least one outstanding property. Most of the time, people get confused. High performance fibers means high strength fibers. That is not always the case. We have seen many fibers which are not very high strength, which are not very strong, but still they are now being classed or called as a high performance because at least they have one outstanding property. Conductive anti-static is a very good example. We are working on a lot of yarns, which we are making it conductive and anti-static in nature by blending 2%, 3%, 4% of carbon polyester-based fibers, And most of the time, there are a lot of applications where chemical treatment can also offer you some good advantage. But we focus mostly on inherent FR materials. But again, chemical treatment materials have got huge market space and there's a huge research going on that we'll cover in the next lecture. Most of these fibers are classed as either thermoplastic or non-thermoplastic. So very basic I have covered for students. Thermoplastics often soften when heated up, melt, can be extruded into fibers. The examples are polyphenol sulfide, aromatic polyester, PEEK. We will showcase some of the case study. Non-thermoplastic, obviously, which tends to char, brittle at high temperature. Even cotton can be a good example. Or for high performance, we have pararamid, metaramid. All these fibers are non-thermoplastic. So for protective textiles, which is our area, here for us, strength is one requirement. Sometimes we need strength, but most of the time we are looking for thermal stability. Most of the time we want our materials, our yarns to be thermal stable. That means they should not degrade under the influence of heat. Say we are keeping a glove at 180 degrees centigrade or 200 degrees centigrade for 50 hours or 100 hours. It should not lose its cut performance or heat performance. So for us, thermal stability is very important, or I will say on top of strength. And so this slide just to give idea, these are the most of the fibers being imported into India. These are the fibers most commonly being used. Obviously, we are into ring spinning, so I have showcased only staple fiber. A lot of filaments are coming into India, and very basic, I have explained why these fibers are used, whether it's for impact, whether it's for fire, whether it's for chemical resistance, and we will try to cover some of these fibers and some of the challenges. What happens when you blend monoacrylic with aramid? What happens when you blend FR viscose with aramid? What happens when you put certain percentage of PBI? So yes, so far I have explained high performance fibers, but now, like I said, high performance textiles can be made using small percentage of these fibers blended with conventional fibers. This is going to be a future. This is going to be very interesting for India because we have a lot of natural fibers with us. Cotton, wool, we have polyester, we have even certain variety of nylon is being manufactured, and a lot of products can be developed, and we can do a good export business as well as domestic business by focusing on how we can make high performance textiles. So two examples I have quoted here. One is brown cotton. Brown cotton, the natural problem is strength is lower than normal cotton. So what we have done, we have reinforced with ultra high molecular weight polyethylene in core. So the final yarn looks brown from outside, but inside we have a reinforcement of HPP, which is making it cut resistance. And with Silcot, we are doing a lot of work on making a fabric, and we are trying to develop some uniforms where you don't have to worry about dyeing. You can just do some finishing, and you have a naturally cotton. Another best example is uh, polyester blended with anti-static stainless steel fibers. So we are doing draw frame blending. These stainless steel fibers are not easy to process because we are talking about 8 micron to 12 micron of stainless steel fibers. So again, this is a very good example. You have 90% of traditional polyester, which is easily available, and you are blending with 10% of stainless steel fibers. And so here the two important areas are there. One side, how we can make stainless steel fibers in India, how we can convert 20 micron wire to 8 micron fibers. And second thing is how we can develop product. So I mean, these two examples will show you that hardly 10% or 20% of high performance fibers are blended with conventional fibers to make the whole textile high performance. So this is what our company does. We have two verticals. So one side we are designing yarn for protective textiles. Here we are using most of the organic fibers which can be used next to skin. And then we have an insulation segment where we are using variety of inorganic fibers for insulation. These are the yarns mostly it's used for protective textiles. And we have got few patents. And like I said, it's very important to manufacture, but it's more important to test your product not only as per the international standard, but better than that. So with this, keeping this in mind, we are working on developing variety of testing machines, which performs as per ISO standard, but we are adding additional components. This is the best example. We have modified our TDM cut tester, where we are able to do cut testing at higher temperature. You know, on the insulation side also, we are doing a lot of insulation projects for automotive. Here also, we are trying to develop testing machine where we can test sound and heat insulation both at the same time. These things are going to be very interesting in future. So then we have testing lab. Once again, our vision for this testing lab is to speed up the development. So you have a yarn, you have a product developed, and you want to test it like yesterday. You don't have time to wait for test report for 3 months. So that was the reason. That's how we created a lab, which is not only helping HPT, but it's also helping many companies for the product development. And we are working with NABL to get it accredited in future. So yes, coming back to our topic. So we are going to focus on these fibers. And as you can see, what's the problem? What's the challenge? Why it's so challenging? You can simply have pararamid fiber, you can make yarn, you can make fabric, you can export it. What is the problem? But here is the problem. Now we have almost 7 to 8 brands of pararamid fibers available. We have 5 brands of metaramid fibers available. We have 3 brands of modacrylic. We have 3 brands of viscose. So every fiber is having multiple suppliers. Okay. Now imagine you are buying a yarn or you are doing a research where you are blending 3 components, and then you have steel, you have glass. So it becomes so challenging to validate your raw material. So what are the challenges, how we can, process it. So this is just to give you an idea, the level of complications we are seeing. And this I've just mentioned all virgin, then you have recycled. A lot of recycled materials are coming to India. And again, it's a fantastic thing. We should work with them, but we should be able to test our material. So, I mean, just few slides I have given for students. I don't want to get into the deep chemistry, but very basics. What are liquid crystalline organic fibers? Why it's so high strength? We all know it's a different phase between solid and liquid, and The segments are methogens. So, we will be sharing this slide so students can read and they can make notes and they can understand the basics, and we can discuss, these things in detail. So, LCPs, most commonly these two liquid crystalline polymers are available in the fiber form. One is lyotropic, other is thermotropic. Lyotropic is basically based on concentration of liquid crystals. Aramid is the best example. Thermotropic, aromatic polyester, Vaptran is the best example available commercially. And I've tried to explain why aromatic polyamides are different than nylon. I remember when we started in 2010. At that time, customs in India, aramid used to be classed as a nylon. So while importing, there was no separate category. It was being imported with the same HS code as that of nylon. So you can see the similarity. The only difference is it's having benzene rings, which is what making it more strength, more thermally stable. And again, why it cannot be melt spun, because the materials decompose before the melting point. So most of the time they are manufactured using wet spinning, which is another challenge. Two types of aramids are very popular in India, metaramid, pararamid. We have different suppliers, and we'll be covering dye finishing also of these two materials. And just to give you an idea, as a spinner, for us, density is very important. You see, pararamid density is 1.45 and metaramid is 1.38 and PBO is 1.54. So after carding only, we can work out the difference, and you can see the fluffy nature of metaramid. Not only that, when we are reinforcing tungsten or steel wire, so the percentage of yarn changes based on the density. Although it's a common sense, but for textile yarn guys, sometimes understanding that tungsten density is 19 gram per centimeter cube, whereas your fibers are 1.45. So it becomes interesting to find out the exact composition of your yarn when you have materials of different density. So imagine you have a yarn which is ultra high molecular weight polyethylene, which floats in water, and you are making a tungsten based yarn. So you have two different density material, and you are blending it and you are trying to make yarn. So it becomes very interesting. Aromatic heterocyclic fibers are also there. Again, PBO is best example. PBI is also most commonly used in protective textiles. I will share some case study on this. Um, PBO is an interesting fiber. Unfortunately, these are not being used in protective textiles. We'll see the reason because its conductivity is very high. It conducts heat, but PBO is very much used in mining, for mining belts, or high temperature applications where you don't have to touch it. You don't have to. It doesn't come in contact with skin. Again, it's very costly fiber. We have made yarn, and we are doing a lot of research on blends of PBO. We are trying to add 10% of PBO with our yarns just to see, um, how good it is. So this is one slide just to show comparative study of 100% metaramid versus PBO versus Kevlar versus blends. We'll see this testing after lunch. We'll demonstrate this for offline people who are here. So you can see the thermal conductivity of PBO much higher, and that means if you are wearing a gloves manufactured using PBO, you will feel the heat very quickly. It transfers heat very quickly, and that's the reason I can see that PBO is not used in protective textiles. And another fiber is PBI. This is coming up. I'm sure you will see lots of PBI blended protective textiles in India. We are also doing R&D where we are blending 30% PBI with 70% pararamid. And the reason is interesting. First of all, low thermal conductivity, and strength is low, but it's blended with pararamid or metaramid to take care of strength issue. Um, it comprises nitrogen, so which makes it fire resistant, and it is interesting fiber. we are going to get 100 kg of TBI in coming months. So we are going to do a lot of trial and we'll share the result. India also, Gerda Chemicals, they have made ABTBI. We managed to get some filament. We chopped it, we creamed it, and we blended with pararamid. And we managed to make yarn out of that. And trust me, it's not easy to crimp and cut a filament to make it spinnable grade. We have done it on small scale, and now we are trying to get bigger lot. We are trying to get 100, 200 kg so that we can conduct a proper bigger trial. But the properties are very interesting. We have managed to compare all thermal properties by making gloves, sleeves, woven fabric, non-woven fabric. We have made all these in a small scale, and we are finding interesting contact rate transmission result, which is all comparable. But like I said, long way to go before we can get a bale or two bale of these materials and convert that into. But yeah, this is interesting work happening with this ADPVI in India. Polyamide elite fiber. The best example is Carmel. Again, Pushpinder sir has done a lot of blends with Carmel. He will discuss Carmel with alpha viscose blends. Again, very good fiber to work with. Available in different colors, and like I said, it's mostly blended with alpha viscose or sometimes 100%. And it's an example of polyamide amide fiber. We have another polyimide fiber, which is different from polyamide amide. P84 is the best example. We have also secured from another supplier. We will be discussing all this case study after lunch. Each of these fibers, and this fiber is very interesting for cryogenic applications, minus 270 to 300. And the interesting part is cross section. This is the multi-lobal cross section, which offers 90% more surface area. And with higher surface area, you can imagine this fantastic product for filtration. And also you can see elongation is 20%, which is much higher, and it can be interesting for certain applications. And you can see thermal conductivity at 300 degrees centigrade. And I'm trying to find out a lab in India which can do thermal conductivity at higher temperature. I know a few labs in US, Europe, but they are very costly. So if anyone is aware of any lab in India which can do thermal conductivity tests at higher temperature, at 500, 600, even I have a requirement where I have to test thermal conductivity at 800 degrees centigrade. And these are the things we need to see. So this fiber is very interesting. Again, halogen free, so environmental friendly, and a lot of it's being used in filtration. And I can see a good future of this fiber. You can see the toxicity, which I find it very important from Indian point of view. We should really give more emphasis on toxicity testing on all our PPs, and you can see the comparison toxicity data as given by the supplier. And now we are working with IIT Roorkee, or we are trying to develop how we can do all these toxicity tests on our own, and so that we can validate our own with our own data. This is a very basic slide just to comparing both, because most of the time I can see polyamide amide and polyimide fibers are confused with each other, but there is a difference, and this slide is just to show you briefly the difference between these two. Liquid crystalline aromatic copolyester fiber. So far we have discussed lyotropic LCPs. This is example of thermotropic liquid crystalline fiber, which is commercially available. All these fibers, whatever I'm talking here, these are commercially available. So you can buy 1 ton, 2 ton, 10 tons based on requirement. Vectron is an example, very good material. This is the only fiber I have seen where strength increases when you go minus 20, minus 40, minus 60. Now, again, we are working on validating this claim. I have seen this in literature, and we have got material now. So we are looking deep freezer where we can hold it for minus 40 degrees for some time and confirm whether really there is an increase in strength. at negative temperature. But you can see it's a aromatic copolyester fiber, and this is a fantastic example of thermotropic. So you can do melt spinning, and another interesting thing, Bactrim is being used in aerospace because of its excellent outgassing and off-gassing uh, uh, properties. That means release of chemicals in vacuum conditions or release of chemicals at high temperature. Once again, we need to do our own R&D to validate these claims, because I'll show you this example. In this example, we performed a basic flammability test and we found some surprising results. Again, we are cross-checking, we have ordered new lots, and we are trying to understand why it's happening, why it's giving very good result in surface ignition, and slightly doubtful results in bottom ignition. So all I'm saying that we should do our own testing with the material. It doesn't matter from where it's coming, it doesn't matter who is manufacturing, but we should do our own validation, because sometimes there's a problem in a certain lot, which can be a problem for you because these are very costly fibers. Um, PVC, again, I like this fiber a lot because, again, it's not very costly. And chlorofiber is blended in a lot of yarns we design. And the best part of this fiber is it's not only low thermal conductivity, but it also has low heat capacity. That means it absorbs and transfers least quantity of heat. So this fiber is also very interesting, and I'm surprised why nobody in India is manufacturing this fiber. I think this is not very difficult to make, and there's a lot of market available for this PVC fiber. And you can see that LOI is very high. And here also you can see that LOI is high even at the higher temperature. So you can do LOI testing at room temperature, but then it's performing better LOI at higher temperature. So all testings are done at room temperature, but then also at higher temperature to check the extreme condition. So you can see the trend, which we also need to follow. Again, there's the one demerit that it produces hydrogen chloride gas. So whenever you design protective textiles using chlorofiber, make sure it's hidden inside, make sure it's covered with other fibers, make sure it's not going direct in contact with heat, so that you don't have this problem of hydrogen chloride. So like I said, it's very interesting fiber, and for certain applications, it's giving very good sound absorption results due to amorphous nature also. Kymol is an example of novolite fiber. We have just secured 50 kg of this fiber, so we will be making yarn by blending with different material. But the best part I like about Kynol or novolite fiber is 76% carbon. So this fiber, after being converted into fabric, we can look into making semi-carbon fabric, with certain applications, and that will be very interesting. So again, very interesting fiber to play with, to look into. It's low thermal conductivity, and it's already being used in certain application. Again, smoke is interesting for this fiber. If you are looking for something, especially for inside aeroplanes or inside closed area, Kynol can be very interesting, or novolite fiber can be very interesting because the smoke generation levels are very less, shrinkage is very less, and obviously because of absence of nitrogen, sulfur, does not contain any toxic components. Carbon and semi-carbon fibers, again, not a new fiber. It's being used in India. A lot many companies are making products out of semi-carbon because these fibers are not very costly. You can get free of fibers or open fibers in the range of $5-6 a kg. But the challenge is converting it into yarn. This fiber is very brittle in nature. So the moment you put in carding machine, you will start a lot of dust, powder start generation, and a lot of contamination. So even we try not to use this in a bigger proportion, but it's very good fiber. And in India, this fiber has been developed. We have got 20-25 kg of this fiber, um, which we are going to do another trial. We did one trial before, where we blended this fiber with aramid and developed the yarn fabric. And now we have got around 50 kg we have got to do another trial. And this fiber, hopefully, this will be available in India for further consumption. Apart this cost, again, it's very interesting fiber. It's being used in many protective textiles applications. And there are 3-4 types of FR viscose coming into India. We have Lenzing is there. Now we have Graphene also started manufacturing this. And main property is it generates phosphoric acid, main decomposition product. And like I said, for researchers, it's very important to develop or understand, have understanding of FR viscose fibers, because from October next year, we'll have a QCO coming up where it will be mandatory to use FR items for all commercial, applications. So you'll see sudden increase in demand for these materials. So it's very good fiber to look into. Modaclick, again, those who are into protective textiles, it's not a new term. Last 20-25 years, it has dominated with cotton blended material. Protex cotton is a very most commonly used work wear uniform. And we have sir who must have processed over 2,000 tons of Protex in his career. It's again a very interesting fiber. A lot of new developments happening. We are going to get new lot of fibers which is smoke free. Again, 2025 is going to be very interesting for Protex. Polyacrylate fiber. Again, we bought this fiber 50 kg 1 month before, and we are finding it very interesting when we have blended with aramid. And you can see that the moisture absorption is 27%. So it's very comfortable. And what we have done, we have developed the 2 blends, and we are doing a lot of testing. We are comparing these fibers with other materials, and you will see some polyacrylate fibers being used in India very soon. So what we have another speaker at 10:45. So what I will do, I will stop it here, and once after Manorma ma'am's lecture, we can again I will continue my session, because I really want to cover, and I'll need another 30-40 minutes more. And so we can, we have HPP, we have Basalt, then we have some automotive, e-glass, ECR, polycrystalline, metallic fibers. Then, so yeah, I really want to give more time on this. So let us, Shubham, we go for the second sir, and then in the end, I will conclude my session. If there's any question, I can take 1 or 2 questions. Otherwise, we can take question at the end of, after ma'am's lecture.
Sir, like I said, both sir.
All like that? Okay. So let's start with the second. Thank you. He's trying to speak our Sorry?
Hello, sir. Am I audible, sir?
Yes, sir. You are audible, sir.
Yeah. Sir, this is Pramod, a research scholar working on textile reinforced concrete. Can you please throw a light on alkaline resistant glass fiber net, if possible, sir?
Sorry, sir.
Can you please repeat your question?
Sir, can you please throw a light on alkaline resistant glass fiber net, sir?
Glass fiber net.
Sir, am I audible, sir?
You are audible, but voice is not that clear. You are saying arc flash protection.
Sorry, sir, I didn't get your word.
Can you just chat your message your question in the chat box?
Sure, sir, I'll message here, sir.
Thank you, thank you. Like I said, I'm here. We'll complete the lecture. Then again, I'm here. So feel free. So I just want to start the second lecture, with the host then, and then so I really want to keep it on time for everyone.
Hello, Shivam. Hello. Are you able to listen to me, Shivam? Hello. Hello.
Sir, audible, sir.
Yes, sir. You are audible, sir. We can hear you.
Yeah, is it audio?
Yes, sir. We can hear you.
Acha.
So Shubham, you can introduce, sir, and then sir will start. Okay. So just a second, Shubham will introduce you, and then we can start the session.
No problem.
Professor Yes Ghosh, sir, a graduate from Calcutta University and a PhD holder from IIT Delhi, is a leading expert in mathematical modeling of fabric formation processes, water filtration, and medical textiles. Over 34 years at NIT Jalandhar, he played a crucial role in establishing and advancing the textile technology department, with more than 50 research papers published in prestigious journals and conferences. Professor Ghosh's academic contributions are exceptional. He has supervised over 10 PhD students and conducted a research visit to Australia for wool development. During his PhD at IIT Delhi, he has instrumental in establishing a state-of-art knitting laboratory. Ghosh sir, please continue, sir. Sir, please share your presentation.
Just. It is just.
বলো তো কেন সিম না স্ক্রিন
ওটা আগে দেখে এখানটা
করতে পারে
এখানে আমি সব বন্ধ করে দিয়েছি তো দাঁড়া এগুলো খোল আগে এই যে
ক্যামেরা
আচ্ছা Hello, is it audible now? Hello.
Yes, sir. Yes, sir. You are audible, sir. And we
Acha.
can see your screen as well.
Yeah, you can see my screen also?
Yes, sir. Yes, sir.
Okay, okay, fine.
You can just make it a slide, presentation mode, sir. You can just make a slide show.
Presentation mode, presentation mode. It, right? Hello? Is all
Yes,
right?
sir.
So,
Sir, you can.
good morning, everybody. Now, I am just telling you. So, this is a very presentation which I used to teach my student, BTech and MTech student on tensile properties, very initial few lectures. As Dr. Nandan has told me to give me some basic concepts on the properties and the philosophy behind those properties. So what are the philosophical concept on those properties? So I'll try to tell you in very simple language some of the things which you may do in your daily life, or you may do your daily testing, some of you, or some of you may have studied, but I will add some philosophy in it, how to think beyond the simple concept which you are having, right? So properties are there. Out of that, you know that why these fiber properties are so important for all of us. Now see that reason behind it. So the mechanical properties of fiber is basically whenever we apply any force or deformation, and then how this fiber will respond, giving the response, and that response is most important as far as textile product is concerned. When you apply some force or some external forces, so we just try to find out, so what is the reaction to that force, and how your fiber is behaving. And all of you know that why fiber properties are in a textile are so important, because ultimately your yarn and fabric, which is a complex structure, a combination of fiber. So ultimately whether you go for yarn or go for fabric, so your fiber property will ultimately contribute to your yarn and fabric property. So until and unless you know your fiber property very clearly, or very clear on fiber and its basic properties, so it will be very difficult to have some idea or predict that how it will behave when it will transform to yarn and fabric. And the mechanical properties of fiber cover a large number of effects, and all of which a large number of effects are there, so which combine to determine the particular characteristics of the fabric, particular character of the fiber. Now I'm just telling you, if you see because ultimately in what London was talking about the fiber, and ultimately you have to convert to a usable textiles, that is your fabric. So when we talk about the fabric, then fabric usually have, we consider two kind of property. One is that how it will behave on mechanical deformation. So we call that as the physical properties of fabric, and another is a flow property. So flow property means when something is moving across, it can be heat flow, it can be air flow, it can be fluid flow, it can be electrical current, any kind of flow across it. So these are the important fundamental property which we deals with the textile fabric, because ultimately fiber will decide the property of your yarn, and the yarn which
Sir,
is from
sorry,
the
sir,
fiber.
your slides are not changing, sir. Can you just,
Now it is changing. Now it is changing.
no, sir, we are still on the first slide.
First slide.
So can you just, we are just saying your first slide, we are just seeing your first slide, tensile properties of, after that it's not going. So can you just make it in a slideshow mode,
No.
full screen, huh?
बता दो नीचे वो tap करके.
So can you just make it in
फोन करके.
sir, Shubham is just calling you on phone, sir.
Right.
Yes, sir. Now it's changing. It's changing now. I mean, just now it's gone to second one, but you can just click on
Now
the.
it's changing.
Yeah. Yes, yes.
Yes, sir. Now it's changing, sir. Yeah, now it's there.
Now see that
Yes,
it's
sir.
changing.
Yeah, now we can see the tensile properties slide. Yes, sir.
Uh, So this slide I was talking about the mechanical properties of textile fiber. Why it is so important? Because ultimately textile woven fabric we consider two important properties. That is the how it is responsive to mechanical deformation or mechanical forces, or a flow property which deals with mainly with your air flow, water fluid flow, heat flow, or the how it is transmitting electrical current carrying behavior of the fiber. That is what mainly we are talking about too. And these whatever property we talk about the fabric, so it comes from the fiber. So until and unless you know your fiber correctly, so it will be very difficult to design a required fabric. So in order to understand your fiber, textile has a lot of problem. If you, in your physics, you have studied the mechanical behavior of the materials. So that is usually engineering or steel materials. So which behaves like a standard law of there. But the textile materials doesn't behave like the standard Hooke's law or standard physics, whatever has been. So we have, that's why we have to understand our material first. Then we go try to understand what kind of material study we can do, or different type of study we can do with this textile fiber. So what is the problem for our fiber, right? Now this slide is visible. Fact determining the result of tensile experiment. Hello. This side factors determining the result of tensile experiment is visible.
No, sir. Still we are on the tensile properties. And now it's changed. Yeah. Now the factor determined. Yes, sir. Please go on, sir. Yes.
So I think now the fact is that the material and its condition. If you see I'll just tell you the materials about materials initially. Now let us talk about the natural. First, I will talk about the natural material. Three natural fibers. So viscose, cotton, and flax. So let us talk about the three natural materials: viscose, cotton, and flax. These materials are of same chemical origin. They are of cellulosic origin. But you will find that these three materials having a different load extension behavior. Though chemically they are the same structure, but to physical arrangement of the polymer molecule inside the structure, the material behaves in a different way. The three I talk about viscose, then cotton, and then flax. Three natural material of natural polymer, that is your cellulose. But chemically they are same, but physically they are different. The polymer molecular arrangement of the polymer inside the structure are different. That's why it will behave differently when when you'll put in under the testing. So this is the nature. I'll give you another example from man-made fiber. Say for polyester. You know, the polyester is basically a ethylene glycol and terephthalic acid that polymerize the polymers of polyester. Now the same polyester can have different behavior in mechanical deformation. It can be having, we are having low tenacity polyester, medium tenacity polyester, and high tenacity polyester. If it is a low tenacity polyester, it will be blended with a worsted fiber. If it is a medium tenacity fiber, it will be blended with a cotton. And if it is a high tenacity polyester, then you will find it will be using a technical textiles, particularly ropes and nets are there. But the chemical structure is same, but only due to change in physical arrangement of the molecules inside the structure, the behavior will be changed. So this is an interesting part of the textile, that the same chemically they are same nature, same thing, but due to physical arrangement inside the structure, inside the it, and the changes are there in their behavior. So then I'll talk another, the condition. Textile material is very much susceptible in which condition you are doing testing. So that's why if the condition change, then your result will be changed. That's why we always suggest, or we always said that whenever you like to do testing of textile material, go for standard testing conditions and expose your materials 24 hours before the testing, so that anything with any problem with the materials or the history of the material will be normalized. If any prehistory is there, it should be normalized. So that's why we always said that the before testing, go for 24-hour conditioning in a RH around about 65% and temperature around 22 degrees centigrade. So you go for, if the condition change, then you'll find that your data will change. So that's why the condition also affect your results of your tensile experiment. So material and the condition that affects your results. So sometimes you'll find the same material, why it will be giving the different result. So that's the reason why you can get sometimes different result. So that's why you will have to be very careful whenever you will be conducting your tensile experiment, and your knowledge to be very clear that you are handling a high tenacity, low tenacity, or medium tenacity fiber. If it is there, then definitely its behavior will be different. Then there is you find the dimension and arrangement of the specimen. So you'll find that if the dimension of the specimen is different, so you'll getting a different amount, a different kind of behavior. So it can be affected due to your cross-sectional area. It can be affected your elongation. So then your mean breaking load will be changed. So that's why you should always know that what is the dimension of your specimen, and the length of the specimen will be affecting your behavior of the fiber material. Or if it is a composite specimen, sometime you'll find that a bicomponent fiber or bicomponent yarn, then it will be depending upon this how this particular bicomponent yarn, fiber or polymers are arranged inside the fiber, that will be affected your testing data. So that's why whenever you'll be using a textile material, or try to compare something with the others, don't go blindly that this has got this strength, this has got this strength, so it will be lesser. Or so you cannot compare, because it may have a different kind of cross section, it may have a different kind of length you have tested, or it may have a bicomponent. If it is a bicomponent in nature, you may have a different arrangement in between them. So the arrangement is also, these three things will decide what will be the result of your tensile experiment. The next other important thing is the nature and timing of the test. The textile materials are affected due to what kind of testing or you are doing basically. Specifically, the elongation, load elongation is not a single valued function of applied load. If it is a elastic material, in our physics, we know that it is a single valued function of applied load. If we applied load, it will deform. If we remove load, if it will come on the same path without any energy loss or without any loss of energy. But textile material behaves in a different way. It is not a single valued function of applied load. Textile, it depends on the length of time for which the load applied, or it will be any previous load has been applied on it. So it will depend. There are two things, which is a length of the time on which load has been applied, or we have applied any previous load, then your result will be also different. So that's why will be doing the test of textile materials. You'll be very, very careful what kind of testing you want to carry out. As I'm telling you, if we want to go for a tensile strength, then we go for a quasi-static testing. That means we try to break the specimen within 20 plus minus 2 seconds. That is our quasi-static concept of quasi-static testing methods. So if you want If you want to test a material, we try to break it within 20 plus minus 2 seconds. Then you can say that this is almost static. So that is how then that tensile data that information will be considered as a tensile deformation. We do the tensile deformation and tensile related data will be generated from there. Now, if we applied a constant load on the fiber, then you'll find that with time its extension changes. So with time, we apply, say, suppose we take a specimen of fiber and we applied a constant load, and it could keep it time, and you find that with time its extension will be changes. So this is a time dependent deformation of your textile fiber, which is not there usually not there in your engineering material. Then there is another one, another kind of, if we suddenly extend a material and a fiber and keep it there, you will find that textile material slowly, the stresses which has developed inside it, it will decay. So the timing also affect. If it is a constant load deformation, we call that the creep behavior. That particular study in textile we call the creep behavior of textile material. Creep behavior of textile material. If we go for a sudden extension and then we see how the stress is decaying on the material, we call that stress relaxation. And the fourth one is the study that instead of static loading, if we applied a dynamic load, that is sinusoidal load, that is E equals to E0 sin omega t, we can apply the sinusoidal load also, and that kind of we call the dynamic testing. So depending upon your requirement of your particular material, you have to select which particular test you want to carry out. It can be tensile load, tensile test, where you will have to break the specimen within 20 plus minus 2 seconds, quasi-static loading. If you want to creep behavior, then you have apply a fixed load, and then you have to see the behavior, how it is changing with time. That is the behavior, how extension changing with time. If it is a stress relaxation, then we apply an instantaneous extension, and then eventually we see how the stress is decaying with time. And if you want to go for dynamic testing, then you have to apply a sinusoidal stress or strain on the system, and then we have to study that what kind of behavior. So depending upon the testing time of your test will be automatically different. It can be tensile behavior, then 20 plus minus 3, then constant creep behavior, then stress relaxation behavior, and then your dynamic testing. So anything depending upon your requirement, you have to decide which one you like to do it. Right. Now, this is a load extension or stress strain curve. Is it visible? Or...
Yes, sir. It's visible. Yes, sir.
So this is an interesting part. Now see that usually textile people talk about the load extension. The mechanical or physics people talk about the strain, and we talk about the specific stress strain. But interestingly, we can convert a load. Our machine usually give it load extension curve, and we can convert the load extension curve into a specific stress strain curve and stress strain curve if we have some data. So now this is I'm telling you, if we apply a load, applied load, then you'll find the extension will be there and elongation, and ultimately you'll find load will be increased, and a time will come it will break. So at the breaking point, we call whatever the load is there, we call that the breaking load, and whatever extension is there, we call that as the breaking extension. Usually breaking extension in millimeter we measure, and breaking load in terms of Newton. So now, so extension can be easily converted into strain. All of you know that strain is the change in length delta L by original specimen length. So we can convert strain and extension percentage multiplied by 100. So we can convert easily the load extension curve into a strain or extension percentage curve. And as far as the specific strain, Specific stress is basically specific stress in our textile. We call it as the tenacity of the fiber. Tenacity and specific stress is same. So if you know the fiber denier or fiber text, so you divide the load with your tenacity value or text value or denier value. You will be find the Newton per text or Newton per denier. In the y-axis, you will get the Newton per denier. And if we apply, if we want to convert into stress, means this is in the physics what we call the stress means Newton per millimeter square per unit area. What is the force? That is why the modulus for modulus, Young modulus are calculated, basically stress. So that we convert, that we can also convert the same curve if you have the data. So that data is required only your density of the fiber. If you know the density of the fiber, then stress equals to specific stress into density of the fiber. So through this interchangeable and interconvertible. So we'll get it usually in the machine. Usually we get a load extension curve. We can convert, if you have the denier value, you can convert into a specific stress strain curve. And if you have the density of the fiber, and then you can convert into a stress strain engineering, what we call engineering stress strain curve, right?
नहीं नहीं कर कर
नहीं घर में आती हूँ कपड़े धोने के लिए, कपड़े धो के
अभी मैडम अभी मंदिर गई है
अच्छा
अभी मंदिर गई.
So specific stress is your, as I said, the specific load by linear density of the fiber, and stress is your density of the fiber multiplied by the specific stress. So that's the simple interchangeable convertible. If you if you know that interchangeable, if you put it in the same unit, so you will get the Newton per meter square engineering stress value of a textile fiber. So the other than breaking load extension, there is in textile some of the area where we may not require the breaking load value, because depending upon use, we are having a different kind of measurement technique. So one such technique was a work of rupture. So work of rupture is another concept where the elongation necessary to break the useful quantity and term the breaking extent. The work of rupture, individual fiber, we find the work of rupture, we call also the toughness. It will particularly important when we are going for a repeated number of cyclic loading on the material. Then we go for a work of rupture. So the work of rupture is calculated basically if we go for a load extension curve. So ultimately there is a breaking load and breaking extension, and if we integrate over that, or the total area under the curve, we call it a work of rupture. So this work of rupture is important when we talk about the cyclic loading. When we are going for a material which will be used under cyclic loading and continuous, when we don't go for a breaking strength of the material, but instead of that we apply a load and continuous cyclic loading on that, and then we will find out that work of rupture of that material will be more important than that of the breaking load and extension of the material. So now let us talk about the few things, because textile material usually do not behave like a steel or material. So that's why it is very difficult some of the time. But if you go for a magnification, larger magnification, in the initial portion, it will almost having some amount of linearity in it. So if you go for an initial portion of the specific stress strain curve, then there is the initial portion having a linear, then we draw a tangent from there. And if we draw a tangent, from that tangent, the modulus will be calculated from the value of tan alpha, which is basically will be equals to your stress by strain. Nothing but tan alpha is nothing but it will be a stress by strain. If you can find out, if you have a curve like this and draw a tangent of that, then that particular from that tan theta value, tan alpha value, you can find out the modulus of the material, and we call that as the initial modulus. There are many modulus are there. There are many modulus are there. This modulus we call the initial modulus. From the origin, we draw a tangent. So then there is a modulus sometime used in a textile. We call this second modulus. Then at that time, what we do? We fix the strain value at 2%. We fix strain at 2%, and then draw a tangent from there. And that from there we can calculate the whatever the stress strain is. From there we can calculate the second modulus. Then we can have a dynamic modulus of the material also, and also the creep and stress relaxation modulus. So all kind of modulus are there, but mainly we are talking about here we talk about the tangent, the initial modulus of fiber, so that you will be having some idea. So how much elastic nature textile materials are there, and how much it is deviating from there. And second modulus will be helping us. Second modulus will be helping us that the usually textile material is not more deformed up to a 2% of the fiber. So what is the stress strain ratio at that particular value of modulus? So now there is another one in our physics we call the yield point. So it is very difficult to find out the yield point of a load extension for a particular textile material, but here this has been given one concept of how to find a yield point. So after that it will behave like a elastic material. After that it will behave like a non-elastic or viscoelastic material. So here first you have a load extension curve or stress strain curve, and then join a dotted line from origin to breaking point, right? So after that, you draw a parallel lines on that, of this particular line, and a point will come when so it will be bisecting, this line will be bisecting the curve in 2 points. So ultimately, if we go on drawing, the time will come when a line will be just having a tangent to the curve. And at that point, where it is become a tangent, at point we call the yield point. And whatever the stress value was there, we call that as the yield stress. And whatever the strain value is there, we call that as a yield strain. So how we can find out the yield point of a textile material. Is very difficult in case of our engineering material, is a clear-cut point from where it is from elastic to non-elastic region. But in textile material, find difficulties. But this is one of the technique which is been explained, that you can find the yield point of a textile fiber. So then the crimp of the fiber, how you can find out the crimp of the fiber? You take, if you want to calculate the crimp of the fiber, you take a fiber in crimp, whatever the crimp condition length, then you put on a load machine, and then you draw a curve, you will get a curve like this, and then you just extend it backward at point O, whatever the at point O, A to O is your crimp value. So you'll find that is the length, which is in the crimp condition length. So from there you can find out the crimp percentage of your fiber. So these are the some typical curves, how the stress versus extension of a nylon, polyester, carbon, glass fiber, aramide, and steel. You will find that out of all these fiber, they have a different kind of behavior under load. And that's why they have a entirely different kind of user there. So nylon is having the highest amount of extension, and nylon and polyester, and you see that steel, carbon, aramide, they have the very low extension. So depending upon your requirement, they have a very high stress value. So depending upon your requirement, you have to select the fiber. So whether you go for any use where extension is most important, then you have to go for nylon. You are going for a use where your strength is important, then you will have to go for another set of fibers. So that gives you the very clear-cut picture. So selection of fiber depending upon your end use. So if it is extension-based use, then you have to go for a nylon or polyester. If it is a strength-based, then you have to go for aramide, glass, silver, steel, or in natural fiber hemp is here. So I'll be giving you one. This is a generalized diagram very from wool to flax fiber. So all textile fibers are in this domain. You'll find. So they have a kind of behavior. Wool is of the textile fiber. Wool is one of the highest extensible fiber. If you know that it has a high crimp in it, and that gives you the very high extension of the wool fiber and very low strength. That's why, as I told you, to blend with the wool fiber, you need a low tenacity polyester fiber. That time I say, worsted yarn preparing, you need a low tenacity fiber, low tenacity polyester fiber, because load extension curve of wool and low tenacity polyester will be matching with each other. So that if the load extension are matched to some extent, then it will be giving you a better blending possibility and better realization of the properties of your yarn. And that's why wool is never blended with a medium or high tenacity polyester fiber. So that's how your different range of fibers are there, which are having a different kind of load extension behavior. Then there is the terminology, another important aspect of the textile or any material deformation, elasticity. Elasticity, whom we call elasticity. So suppose we deform it by some amount of load. Then we remove the load. Then that material should recover the whatever the extension has been taken place. If it recovers its full amount, then we call that is an elastic deformation. So an elastic recovery, that's why we call that elastic extension, total extension. If the total extension is delta L, sorry, if original length is L and we extend through an amount of delta L, now on removal of the force, if it comes back to L, then it will have to elastic recovery will be 1, and we can say will be 100% recovery. So that is what the common concept of elastic recovery in our physics. In physics, we call it in our classroom physics 12, we call elastic recovery. That is the common definition. But that particular concept is slightly weird in case of our textile, because textile material may recover 100%. But during the process of recovery, it may lose certain amount of energy which is not there in our steel material. So that's why we don't go by this elastic recovery concept, elastic extension by total extension. We try to find out the work recovery. Work recovery, what is work recovery? We go for a load extension curve. Then the work under the forward curve and work under the return curve. So that will decide the work recovery. If we deform the material and then it recover on the same path, then work will be 1. That is the 100% recovery. But if it recover from a different path, that means some amount of energy is dissipated during the process of deformation. And that particular part will be indicated for textile material, and there is a possibility of textile having recovery just like a loop. If it is in the form of a loop, then definitely that elastic recovery concept which is defined in our physics will not be workable, because here the total energy has been, whatever energy has been used for deformation, the whole has been recovered. Now, recovery, then you will find if it is coming on the same path where it is deforming, then it is 100%. If it comes in a different path, then work recovery will be different, because work on the return curve will be less as compared to total work done. And that's why work recovery is important for our textile material. Whenever we talk about the elastic recovery of textile material, we'll go by work recovery, not by our not by our concept of this physics. Now, how this is a molecular model, the viscoelastic material, particularly textile material, how it is behave elastically, how it is behave a permanent deformation takes place. This molecular concept. Say A, B, C, D. This is this indicate a polymer chain, and A prime, B prime, C prime, D prime, another polymer chain, and they are connected through certain bond. So when we apply force, see that the bond that bond will be connected, bond will be strained. If it is in a strained condition and we remove the force, then it will back to A. From B to A, it will spring back. So then it will behave like a elastic. But if our applied load is very high, then the bond at A will break. If you have bond, if the A at A, the bond is weakest one, the bond at A will break. If we apply a higher force, then the weakest bond at A, say assume that A bond is weakest, so the bond at A will break. So that means now the A will form a bond with the B prime. That means this particular extra length, A prime to B length, has been permanently deformed. So it will not be able to recover that amount. So that amount is basically in our, we call the plastic deformation or reformation or link in a new position. So that is how we can define that, how textile material, if you apply a higher amount of load, then the sum of the bond will break and it will form in a newer place, and that particular deformation will be your plastic deformation, which is unrecoverable. And this is the concept, molecular concept. See, there are two polymer molecule, A, B, C, D, E, one polymer molecule. This is indicating one polymer, A prime, B prime, C prime. There another polymer molecule. They can having a interacting bond with it. If we apply less force, then it will be strained. The moment we remove the force, it will spring back to A again. But if we applied high force, then the weakest bond will break and it will form a newer position. And so that ultimately you'll get a plastic deformation. That's the concept of elastic and plastic deformation, which is happening in our textile fiber, particularly polymeric textile fiber. So this is what I was talking about. This. Now see that this is how the plastic deformation, elastic deformation, and we apply, suppose we apply a load. So then we remove the load. So instead of coming back on the same track on which thing takes place, it comes back sharply down. So that means the energy which is here under this one, these these lines are basically dissipated, and only recovered amount is where the nets are there. So the plastic deformation is this part and elastic deformation is this part. So that's the concept, how we can find out the elastic and plastic deformation by using a load extension curve from our testing machine. So we load it by some amount of load. We don't go for a breaking. So then after that, that load is removed. Then you will find the recovery takes place not along the path which the loading has takes place. It will come through another path. So the area under this net is basically recovered. So it is elastic deformation. The area under the other the part which is unrecovered, which is called the plastic deformation. That means the bond has been, in molecular level, the bond number of bonds has been broken and it has formed on a newer place, so it cannot bounce back. So if your load is higher, then it cannot bounce back. And if your load is lesser, so it may be probability of back will be always there. So this is here, this is a repeated, you can go for, this is just a indication that repeated number of cycles of loading are there, and this gives you an idea that how repeated cyclic loading takes place, and ultimately a time will come when the material will fail, and that here the failure will be takes place based on total work of rupture of the specimen. So if you want to find out the failure, at what time a material will failure on repeated loading, so in this process we can find out that we have to calculate the work of rupture of a material, and then from the plastic elastic deformation curve we can find out what will be the total number of cycles a particular material can withstand before failure. Now this one is for better understanding. You see that we apply load, it follow this one. Then when we remove the load, it come back and come back like this. And so it is a immediately recovery and total recovery like this. And this is the amount which is this is the inside amount which is left out, is the basically energy which is lost during the during deformation, and gives you a permanent extension to your material. So I just, as I said, that creep behavior, here you see that creep, in that creep behavior, I just give you in brief. So in creep, we apply a constant load on it. And then we see that how extension is changes with time. In creep behavior, we apply a constant load, see how the extension changes with time. See that, so it will be having a extension. After that, now with time, it will be having a go on extending or go on extending. So this particular behavior, the changing of elongation or extension of material with time, is your creep behavior. And you see that in stress relaxation, we give instantaneous extension here, and stress will develop inside the specimen. And if you go on, that extension remains same over time, then it will feel that you will see that the stress will decay slowly with time. So these two are the study different kind. If your material has to be used under creep study, certain load and longer time, so then you have to go for a creep behavior of the material. And if you go for a fixed amount of extension and it will be there for forever, then you have to see that how it is behaving with the, how the stress is decaying, whether stress is decaying. If it is an elastic material, the stress will not decay. If it is an elastic material, then extension will not take place with the, if we keep on load for infinite time, then there will be no extension. Now there is a difference between elastic and our viscoelastic material. Suppose in creep experiment, we apply load, extension, instantaneous extension is there. So after that, there will be no extension with time for elastic material. But our material will go on extending with time. Similarly, if we extend it instantaneously, then stress will develop in elastic material and it will be remain same throughout the time. But our material will decay slowly with time. So and the reason behind it in both the cases I'm telling you. So if you see the molecular concept which I said to you, if we hold, if a load is there or if a extension is there and we hold this specimen there, then slowly the weakest bond are there. Wherever the weakest bond is there, it will break. And it will form the new bond at a newer place. And that gives you a permanent extension. So that's the reason why we go on extending with time or go on decaying with time. So it comes from the molecular concept of weakest bond at any place will break if you hold it, and ultimately the stress will decay for that, or you'll find that go on having extension and there will be no recovery from there with time. So these are the two different type of other than tensile. This is how we study the creep. If you apply, if you are going to use your material, yarn or fabric, where creep is important, then you have to do the study in this way. If you are going for a material where it has been used, you have to see the stress, how stress is changing with time. Then you have to do the stress relaxation behavior of the material. So these are the two different. And as far as the creep is concerned, I'm telling you, creep, as for creep is basically, say, for example, the particular rope. If you use the technical rope is a rope, you have to study the creep behavior of the material. So dynamic test, I'm not going to tell you anything. This is how our dynamic testing is there. So usually strain, we apply on it. Suppose if it is a epsilon t at any moment, epsilon, and that is epsilon 0 sine omega t, epsilon is the maximum amplitude. If we apply such kind of strain onto that, then in response to that, you will find out that is a dynamic analysis. So it is only where the dynamic concept, dynamic application, your material will be under dynamic stresses or strain. Then only you have to go for a dynamic analysis of the material. So then I'll just end with I'll just complete with the two sides. So this is about the mechanical properties. Now I'll talk about the thermal properties of different materials. So you can have some idea how to design a technical textiles fabric. Or if you suppose here is the range of our textile fiber. And say the thermal conductivity material. The copper, you know that copper is the one of the best conductor as far as the heat is concerned. Copper is 380 watt per meter Kelvin. Cotton is 0.071, wool 0.054, nylon 2.250, PET 0.140, water is 0.5, and air is your 0.025. So these are the range, some of the range given to you, and that gives you concept. Suppose if you want to design a textile fabric with a insulating material. Now all of you know that we use wool, and see that wool is a fiber which is having a very lowest value of thermal conductivity when you compare to copper. And steel here is having a least value of conductivity. And textile, whenever fiber is a solid material, but when we talk about the textile assembly of fiber, that is your fabric, so it is a combination of solid and air. It's not so it is not the fiber. It is this combination of solid. That means it will be a combination of solid and air. And a combination of solid and air give you the ultimately that particular thermal conductivity of that particular material. So if you have the knowledge of the mixed material conductivity, and if you have, because neither the cotton wool conductivity nor the steel air conductivity will be useful for you, you have to have knowledge of mixed material conductivity, solid and air combination. So that if your textile material is designed in such a way that the air inside the textile material is steel in nature, so that will give you the highest value of highest value of thermal conductivity, lowest value of thermal conductivity, that is 0.025. If it is a steel air, so that means you have to design, if you want to design a low thermal conductivity material, then you have to understand you have to understand the mixture material, joint thermal conductivity, with the aim that the the pores inside the textile material or inside the textile structure should be such that the air should be still, so that it will be giving you the lowest value of the as minimum as possible, very near to a thermal conductivity. So that gives you the idea that how the mixed material thermal conductivity can be decided depending upon the how you are entering steel air inside your textile material. So that will decide your how the thermal behavior of your material will be there. And when they're depending upon that, because as you see from here, textile will never be used as a good conductive material, thermal conductive material. It is basically a non-conduct, the thermally poor conductor, and that's why mainly we use this as a heat insulating material. And you know that our quilt is one such design which is based on solid air combination, and which protect us, all of us, and all of you are in North India. You know very well that what is the importance of quilt, and how because our data is, I'm telling you, we have a research which is here in JTI. Our data is very much incomplete in Indian context, because in winter, on the onset of winter, in the September, October, November, we use a quilt, then we use another quilt add on that, and then we go on another one, or a very thicker one on that. So this is we have to do only because as the lower temperature is falling, so heat loss will be increased, and thermal activity of the material will be such that the heat loss from your body will be standard value is there around 145 watt per meter square. If your quilt can bring that range around 150 watt per meter square heat loss from your body, then it will be protective. Otherwise, you have to put another one on it, so that the heat loss from your body will be coming on that range. So unfortunately, I'll tell all of you, those who are working on technical textile, till now, we don't have any quilt which mentioned the thermal conductivity or the heat loss on a given temperature, given lowest value of temperature. Body temperature is fixed 35, 37 degrees temperature. So at the lowest value, 12, whatever maybe the ambient temperature, room temperature. So what is the amount of heat loss will take place from that at that ambient condition? So that data is not mentioned in our quilt. I think that is a thermal conductivity or the heat loss value when the temperature will be around 10. So that will be good enough for the people to purchase for extreme climate condition in the December and January. But that design is yet to be carried out. So though if you are those who are interested, they can go for we have a paper on JTI. So look on that paper, one in JTI and another in Journal of Natural Fibers. One with a polyester, hollow polyester and cotton, another with a modified jute. So on thermal conductivity research there. So you can, and that research totally aimed for India and Indian context. So can I have a look on that? Those, if someone are interested on design a quilt as per the need of December, when the temperature, ambient temperature, or room temperature coming down almost 10 degrees centigrade temperature. What should be the amount of heat loss? The amount of heat loss from a quilt should not be more than 150 watt per meter square. If you design it, then the people will feel comfortable on that. So that is about the thermal conductivity of part of the material. So, and this is the electrical property. I was just searching electrical property. It is very rarely available. Now I just give you a data only. With the copper, how much you know that copper one of the highest conductivity as far electrical is concerned, and that's what it is indicating, 1.648 into 10 to the power minus 8. This is the volume resistivity of the copper. Whereas textile fibers are highly electrical resistant. So 10 to the power 16, 10 to the power 13. So these are the fibers. So if we want some application of the textile fiber to be used as a conductive material, so you have to coated it with some material, so that the conducting materials will be come into the picture. It will conduct. Or as we are trying to with this non-conducting textile fiber, if we can blend the fiber, maybe your yarn and fabric can be a slightly better conductor as compared to whatever the data has been given here. So that's the concept from where we can have the value of conductivity value of the material can be possible. Conductivity of the, so the option, either go for a blending with the fiber, which this particular Dr. Nandan's company are doing. I'm very happy he is doing something really good as far as the blending of steel fiber with this Kevlar and Nomex and other high tenacity fiber. And then only you can get some amount of conductivity in your material. Or otherwise that you form the fabric and you coat with certain, there are a lot of researchers, they are on coating of electrical conductivity of the textile fabric. So you coat it, and that gives you a concept of your coating element, and that gives you electrical property of the material. With this thing, that's all. Whatever the small thing I thought of to share with you as per the request of the Dr. Nandan. And
Thank you so much, sir. Thank you so much.
I hope
I
that
really wanted to touch your face, sir. Please, we are very happy, and I think after 22 years, 2002, we attended your lecture in third year, and then final year 2003. And I think I have Mr. Harish also. He's also from 2003 batch. So we two students are here, listening your lecture after 22 years. So if there's any question, maybe we can take one or two questions quickly.
Someone has raised the hand.
Sorry?
Someone has raised the hand.
Please go on. Please ask your question. If not, I'll just wanted to discuss this creep issue with sir. And definitely, whenever I'm in Calcutta next time, I want to see you, because we are doing a lot of work on using ultra high molecular weight polyethylene, where this creep issue is very important for submarine ropes, and maybe, sir, we'll need your guidance, or your views, how we can look into this at extreme conditions. Something coming at room temperature, but we want to test it at -10, -20. So can you share some of your experience on this?
Actually, Nandan, I'm telling you that we have particularly thermal conductivity. We have started at NIT design thermal conductivity tester, but somehow just left after that. So what we have done, the upper there are two plates are there, right? We use the upper plate. Temperature, we can change the temperature from around 30 to 100. And the lower plate we connected to a cryostat, and we try to lower down the temperature even below the room temperature. So in that way, we try to conduct the experiment, and we found that the textile material has one problem. The moment we go for a temperature less than 5, 6, 7 degree, less than that, then inside that textile material, there is a condensation of water vapor is there. So we faced a problem that when we just started working on our this particular thermal conductivity, we thought of that we'll go at 0. But what happened then at 4 itself, when 3, 4, 5 degree temperature, see that slowly there is a condensation. The vapor is there. Slowly condensation of the vapor is there, and we found that the conductivity of the material, the textile material, suddenly increased. As the temperature is falling, the conductivity of the textile material is suddenly increased, and it was basically due to condensation of vapor and water having a better conductor as compared to the air and textile. So that's the change what we have at that time. So if, as you said, that if it is a below temperature 0 degree, so then I have taught some of the people. So actually, my brother was a retired professor from Sai Institute of Nuclear Physics here. Physics, he was a professor. So I asked him. So he told me that there are only one possibility. You have to go for a vacuum. Want to that that problems is arising. Then if you put this whole thing in a vacuum chamber and then you go for a testing of it, probably that problem what you are facing, that may not be there. So but that kind of experiment I have not done it. Just an idea, how we can do even a below temperature textile material at textile fabric at a lower temperature. Otherwise this condensation problem will be there, because moisture will be there. As the air is inside it, moisture will be definitely, it will be there.
Yeah.
So
Thank you, sir. Thank you.
so that's what basically that thermal conductivity quilt part. We have tried actually very thick layers. A particular we designed a what do you call it, a thermal conductivity tester, because this standard imported testing machine doesn't have this so much amount of gauge length.
Yeah.
So we use around 5 centimeter 10 centimeter thick layers of textile material.
Right.
And we try to find out there. So in that case, you have to, but once you have started working in this area, my simple idea is that when you design a quilt, it should say what is its thermal conductivity at what temperature, what will be the, if it is at a 37-degree inside temperature, so what is the amount of heat loss if it is in ambient temperature 10 degrees centigrade. If that specification is there, then definitely as a user of say North India and a wide area of North India, as a user, we will be very clear that if this is the condition for 2 months, then we have to use this kind of blanket for that particular period. So that will be, otherwise you have to put, as you know, that a hostel I used to talk when I teach my student of the heat flow, heat transfer. So as the first you use one, then you go for another blanket, then you go for in the month of January for another blanket. So 2, 3 will be there, so that your heat loss from the body will be coming to a comfortable heat loss, so that you can sleep inside it.
Yeah. Thank you, sir.
So,
Over to you, Shubham. Thank you, sir. Thank you.
So I think, Nandan, I think so after a long time, just as you said, you hear from me, I think. So I will try my best, whatever I'm trying at that day also, even today.
You were wonderful, sir. And like I said, I will visit Calcutta and we need to sit down and we need to prepare 5-10 hours long module, This is interesting area, sir. And 45 minutes, 50 minutes is not enough. I have a lot of materials and, we need to do something in this area, sir. With your knowledge and, with the materials, I really want to bring this knowledge to a simple industry people, They should be able to understand what is creep, what is the importance of creep, what is the conductivity at different temperatures. So it's very interesting area, sir. Thank you. Thank you so much for starting this one. Yeah. Shubham?
Thank you, sir. Thank you for insightful lecture, sir. Our third lecture is on dyeing and finishing of flame retardant fibers. This session will be taken by Mr. Khusvinder Dhillon, sir. He is consultant to different organizations, including ITT. He served JCT for a very long time and worked in different dimensions, such as development and implementation of customized solution in technical fibers according to the customer requirements. Fashion wear, work wear, sports wear, adventure and utility wear, smart wear, cut resistance, chemical protection, and fabrics for industrial and defense application. So his enormous knowledge in the field of specialized textile will certainly help us in the product development. Now I request Dr. Kushwinder Dillon sir to start his presentation.
So I will just open the slide. Yeah. I will present in the presenter mode, no? Yeah. Okay. Please, sir. Have it.
Hello, good afternoon to all of you. We will be basically focusing on the processing of inherent flame retardant fibers. Now, let me just give you a background to it. Basically, what exactly is meant by technical textiles? Now, technical textiles is a very vast term, but it can be generalized as nothing but a textile which is primarily valued for its functional needs rather than aesthetic or decorative. They are basically customized and engineered to meet certain specific technical requirements and the performance criteria. Unlike the conventional textiles, and they are valued for high strength and durability, resistance to chemicals, heat, water, wear, flexibility of designs in certain applications, and fire, water, and ultraviolet. Technical textiles is probably the fastest growing area, primarily because the needs of the society are now more diverse and more customized. Everybody wants fabrics depending upon their needs. Now, technical textiles are used in diverse sectors. For example, we have this bulletproof vest, medical textiles, automotive textiles, constructions, agriculture, and industrial applications. Basically, these technical textiles are classified into 12 main categories. One is agriculture, building and construction, clothing, geotextiles, household, industrial, medical textiles, automotive and transport, environmental textiles, and then we have the Malabo packaging textiles. And now what we will be focusing on is the personal protection, that is the protective textiles. And then we have the sports. In the case of personal protection, a human requires protection against cuts, abrasion, ballistic, stab wounds, explosions, fire, heat, hazardous dust and particles, nuclear, biological and chemical hazards, high voltage, static electricity, foul weather, extreme cold and poor visibility, and protection against instrumentation. From here, we will be probably focusing on protection from fire and extreme heat. Now, military personnel, firefighters, welders, molten metal workers, astronauts, race car drivers, all these personnel are exposed to extreme fire and heat. Now, the garments which they wear should protect them against these elements of extreme fire and heat. Now, the garments which are made for these sectors are primarily made from two type of fibers. One which have the inherent flame, they are inherently flame resistant, and these are the fibers like metaramide, pararamide, modacrylic, FR viscose. These I am listing as the most commonly used fibers at the particular moment. Then we have another type of fibers where the fire resistance effect is introduced by giving it a chemical treatment, which is nothing but phosphorus and nitrogen. Now, let's focus on metaramide. Metaramide is nothing for aromatic polyamides, and it is available under different trade names like Nomex, Teijin Connex, Aravin, Newstar, X-Fiber, Caramel, etc. Metaramides, they are inherently flame retardant. They have a good heat stability. Chemical resistance is good. Electrical insulation is also good. Radiation resistance is good. Flexibility, and they have a higher elongation. Metaramides have low thermal shrinkage, and the LOI is 28 to 30%. These fibers are available in the filament form. Then they are also available in the staple form, which we can then, these staple fibers are then used for blending it with others. Now this is also available as a dope dye, and there are also dyeable grade of metaramide fibers. These metaramide fibers have a glass transition of 150 degrees centigrade. They can be dyed using benzyl alcohol as carrier at 135 degrees centigrade. Then after the dyeing is completed, then it has to be washed with a strong soap, and here right first time is the only option, because re-dyeing a metaramide fiber is difficult and far too expensive. Now these metaramide fibers can be dyed in the fiber form. Yarn dyeing, you can do yarn dyeing also, and also the piece dyeing of these fibers can be done. Similarly, even in the blend form, yarn dyeing and piece dyeing can be done. Woven, now these fibers can be woven, knitted, they can be non-woven, and of course now the latest trend of recycled fibers is coming up. Generally, the fabrics made from metaramide are given chemical resistance finish. UV is a degree of UV resistance is imparted to it. Then there may be a certain amount of coating applied to these fabrics to enhance their applications. Now there is a basic difference between dope dyed and fiber dyed. Dope dyed have the highest fastness, be it light, be it washing fastness. Fiber dyed has its own limitations, since this fiber is very crystalline in nature. The dyes, it is difficult to dye, and the dyes on the surface fade over a period of time, and thus gives a faded look to the fabric. Light fastness in the case of dope dyed is to the level of 5, but light fastness in the case of dyed is generally in the range of 3 to 4. Here the dye selection will matter. Washing fastness, you will have to give a really strong wash to remove all the surface dye to get a very good washing fastness. Then we have the pararamide fibers. This is basically paraphenylene terephthalamide. Now these are stronger as compared to metaramide. The heat resistance is good. Dimensional stability also they maintain at elevated temperatures. Chemical resistance is good. Now, para-aramid has one special property, and that is the cut resistance. These are primarily used for making cut resistance fabrics. Cut resistance fabrics which have to be used at elevated temperatures. Primarily, they are available in two colors, yellow and black, but mostly in yellow. LOI is around 30 plus. Again, para-aramid is available in filament form, staple. Generally, I say yellow or black. It is extremely difficult to dye because of its highly crystalline structure. The glass transition is around 240 to 260 degrees centigrade. Now, para-aramid fibers are basically used for protective workclothes, gloves, friction and sealing materials, fireproof blankets, welding blankets, thermal barriers, and fire blocking layers. The brands of para-aramids are Kevlar. This is by far the most popular brand. Then you have Technora and you have Tora. Now, if you see the comparison of meta-aramid and the para-aramid fibers, the significant difference comes in the form of tenacity, that is the strength. Meta-aramids is 4 to 5 grams per denier, and that is 20 to 25 grams per denier. Elongation at break is the second criteria. Meta-aramid has higher elongation at break, para-aramid has lesser one. The limiting oxygen index is almost the same. Decomposition temperature of para-aramid is slightly higher. Basically, para-aramid is introduced into the fabric to give it a higher strength, and of course to decrease the char length. Now, there is another fiber which is as strong as para-aramid, and this is known popularly by the name of Kermal. This is a polyamide imide. Now, this fiber is extremely resistant to acids, alkalis, organic solvents, chlorine bleach, detergents, and is often used 100% in firefighting, where a good amount of abrasion resistance is required. Caramel is typically available as dope dyed. It cannot be dyed. Now, LOI is 32, and spinning caramel has its own challenges, since if you open the bale and leave the bale open, the fiber will lose its crimp. Now, as I say, caramel, it is basically used in blends with FR viscose and many other fibers. Then the most common is one of modacrylic. Modacrylic, the strength is low. They are low strength fibers. They have a high elongation of 28%. It does not melt, but it degrades at 200 degrees centigrade, basically soluble in warm acetone. It is generally resistant to organic solvents, alkalis, and acids, moisture regain of around 4%. Now, acrylic is 100% polyacrylonitrile. If a percentage of polyvinyl chloride or polyvinylidene chloride is mixed to it, that is what forms modacrylic. Modacrylic is primarily around 45% acrylonitrile, and the rest of the component is a combination of polyvinyl chloride and polyvinylidene chloride. There may be a certain additives added like antimony trioxide to it. Now, modacrylic fibers, as we say, they are inherently FR. They are difficult to ignite, but they self-extinguish. They are durable, have a high resilience, and is similar to wool. They are poor conductors of heat, but they are softer and warmer. They have a great dimensional stability and high elastic recovery, generally resistant to chemicals. Now, modacrylic fibers are not subject to insect or mildew attack, unlike wool. They are resistant to ultraviolet rays. They are hydrophobic. Now, since they have moderate abrasion resistance, pilling is sometimes the issue. LOI is around 28 to 32. Modacrylic fibers can be processed in the fiber form, yarn form, and the fabric form. The glass transition temperature is 90 to 110 degrees C, which means that they can be dyed at around 105 degrees centigrade with basic dyes in acidic medium. The general process of modacrylic dyeing will include washing with a non-ionic detergent, light bleach with peroxide and soda ash, and then dyeing with basic dyes and acetic acid. It is preferable to dry the fabric at a lower temperature to avoid yellowing and some amount of harshness primarily. Now this, as we say, fabrics, blended yarns and blended fabrics. It can be blended with cotton, wool, aramid, caramel. Then we have another fiber, which is the flame retardant viscose. Now here the additives are added into this viscose during the spinning stage, and it is made inherently flame retardant. This can be blended with variety of fibers, nylon, modacrylic, thermocool, metaramid, antistatic yarns to create diverse blends. I just come back. FR viscose can be dyed similar to what says in a similar fashion of dyeing normal Malavo viscose. So there's not much of the Malavo. There's nothing special to it, except that in some cases the viscose fiber, if you blend it with metaramid and viscose and dye at 130, there is a chance that viscose may lose its some degree of Malavo property. Then another fiber which is mixed to give some special property to the FR garments is the antistatic fibers. They can be carbon-based fibers, or they can be conductive bicomponent yarns, or they can be polyamides with increased hydrophilicity. Then sheath core bicomponent fibers, fibers with metal salt coating, fibers with a carbon core. Now, one of the general fears is, how do I test whether my fabric has the antistatic fiber or not? The simple is just to rub the fabric on a piece of plastic or a rubber. If it generates a static charge, it will pick up some ash from the ashtray, and that means it does not have the antistatic yarn in it. If it does not pick it up, well, it has the antistatic yarn in that, because it is very difficult for a layman to really test the fabric whether a adequate amount of antistatic yarn has been added or not. The commonly used brands are Bekinox, No Shock, Tamitar, Shakespeare, Thunderon, and Negastat. Now, fabrics in the antistat, this antistat is added to the fabric. Either it can be blended and then added and dispersed all over the fabric, or it can be in the grid form. This will depend upon the end applications. The other fibers that can be easily blended with these inherent fibers are cotton, which has, of course, a very low LOI of 18, wool, tencel, nylon, jute, and ultra high molecular weight polyethylene. The most common blends which are available in the market, or rather they are meta-para antistat, which is commonly known as Nomex 3A, which is usually used in the form of 9352. Then Meta FR viscose antistat, modacrylic cotton, Model-click cotton antistat, Model-click cotton para antistat, Model-click tensile meta para antistat. This is basically trying to economize the earlier blend. And then you have Model-click tensile para nylon antistat, meta Model-click antistat. Now this was as far as inherent flame resistant fibers are there. Now there is another way to impart FR resistance to fabrics is there are in a way two types of chemistry. That is the pyrotex type chemistry, which is generally resistance for 50 washes at 60 degrees centigrade, can be applied to 100% cotton or up to 15% synthetic fiber. Then we have the THPC chemistry, which is 100 washes. Here VAT dyes have to be used, and it can be applied on 100% cotton, and up to 50% of the synthetic fiber can be blended with cotton. There is a third chemistry coming up, which is called the green FR technology. It is at the industrialization stage. It is completely formaldehyde free, safe for intimate skin contact, and depending upon the application, it can be tailored to 25, 50, and 100 washes. Here, reactive and VAT dyes can be used. It is effective on 100% cotton, 100% viscose, and up to 15% synthetic fibers can be blended with cotton or viscose in this. Here, in this green FR technology, does not really cause any pollution. And it is simple to apply. It is simple to apply. It is just pat dry cure, wash and out.
चलो आवाज तो सुन नहीं रही है एक वाइट था ना
then everything. Now this flame retardant workwear is governed by certain standards. The most common are NFPA 2112 and the EN/ISO standards like 11612, 1149, 13034, 1149-5, 11611. These are the common standards which the industry has to follow. Thank you. Any questions?
Thank you, sir. Please go ahead. If there is any question, please feel free to ask.
I have a question.
Wait, let's go. There is one question online. Then we'll go. There is one question from Mr. Rutuja Dongre, sir. Why there is a need to dye aramid fabric given its reputation for high performance application? Which dyeing method is more feasible? Rope dyeing, fabric dyeing, and yarn dyeing?
Yeah. Why is there a need to dye aramid fabric? See, basically the workwear is required in 5 colors. That is yellow, orange, navy blue, royal blue, green, and khaki. These are generally the 6 colors for workwear, and orange and yellow are used in applications where some amount of where the visibility is low and you need to really make out that particular logo person, because the working conditions may not be so illuminated. So depending upon the needs, there are six colors. The dyeing method, the most feasible dyeing method is with the basic dyes. And now there are it can be dyed in fiber stage, it can be dyed in yarn dyeing stage, it can be dyed in fabric dye stage. Now, since these are expensive fibers, wastage is the one which will really impact your cost in a big way. So, and plus, what is the type of machinery that is available with this particular unit? The best would be the yarn dyeing method. The most optimum is the yarn dyeing method. The fastest is the fabric dyeing method, and the best, if we say, is the fiber dyeing method. But
I think that will be cheapest as well.
That is cheapest as well. But you'll have to consider the fact that once you have dyed fiber in stock, then you'll have to consume it in that color itself. Flexibility Flexibility, fabric dyeing. As far as media, good, matlab, best, I would rate is the matlab, yarn dyeing, considering all the factors.
I'll add one more point here, sir. Sir, you have rightly said, we are using basic dyes. But from my experience, for lighter shade, you can try dispersed dyes and high temperature, high pressure setup. But again, you need to do your own R&D, because for some application we were looking for lighter shade, because we were trying to blend it with other fibers, and other fibers were darker in color. So light shade, dispersed dyeing, high temperature, high pressure for meta aramid can be interesting for commercial. That's something a project can be
Yeah.
taken up in future. Yeah.
Next,
Any more question?
The next question was the most economical option for IFR and FR fabric. See here, depending upon the application, you'll have to play with the blends. And you have multiple options, multiple fibers which you can engineer, and all the industry is always working to economize things. And second is it always necessary to add anti-static properties to? No, it is not always necessary. It depends upon the need. Wherever there is a risk of static charge, because these are synthetic fibers, so they will accumulate synthetic charge. So wherever, but per se, general, yes, it is better to add anti-static, or you can try to give it some hydrophilic treatment. If it has a certain amount of hydrophilicity in the fabric, the amount of static charge which will be there will be less.
I mean, here also I would like to add, sir, customer is king. If customer is saying we are particular about EN 1149 part 1, part 3, that means they want anti-static. Even like, sir, we were talking before where you mentioned that you have certain client where they want staple anti-static and they want filament anti-static both in the grid form. So just to make sure that there is no chance of any static charges, so they are very particular about higher percentage of anti-static fibers. So they want some fiber to be blended in the yarn, and then at the time of weaving they want the filament twisting as well. So it all depends on client's requirement and what exactly they are looking.
And see, basically, if there is a very high chance of fire, where there are inflammable vapors in the environment, nobody would like to take a chance with the static charge.
So there is one more question. What would be the what would be the blend ratio for meta-aramid or para-aramid with cotton?
Generally, meta cotton is generally not there. Either it is modacrylic cotton. Meta-aramid is generally blended with FR viscose to give it a level of comfort, and that is 50-50. Meta-aramid cotton blend is generally not very popular. And even if you want to do it, then well, it will be something of the sort of 50-50, because you may want to replace FR viscose with cotton, and you may need to compromise on some amount of cotton and add para-aramid to maintain the particular yarn length.
And maybe the FR treatment.
Yeah, you may need FR with cotton. If you blend meta-aramid, you may need the fabric to be treated with FR. So it is better to go with flame retardant viscose.
Lucky, you wanted to ask a question.
Yeah, I have a question. As we know, as I find concerned, viscose is a regenerative fiber.
Yes.
So how it can be flame retardant? As you said,
Additives.
We add additives in there.
Additives. During the spinning stage, you add some additives.
So at the time of spinning of viscose, these additives are added at the time of extrusion. So you are getting FR viscose. Now we are trying to develop anti-static viscose. So trying to add more carbon. So you can see a lot of things will happen in future where you will see that, it's conductive viscose, you have high tenacity viscose, you have FR viscose, so it all about, new.
As I know,
Yeah.
it is a regenerated fiber and
Yeah.
cellulose too. So how it can be
Yeah.
implemented?
Yeah.
That's why I asked this question.
That's why it's called FR viscose.
Thanks.
Okay, yes, metaramids are from different brands, show a very high difference in dye pickup. Why is it there in the first place? Say, there are two types of portions in a particular fiber. One is the amorphous region, and one is the crystalline region. The amorphous region is the one which is responsible for dyeing, and the crystalline region is responsible for the strength. Now different companies manufacture metaramids to different with different now these companies may be having a different technology to manufacture metaramid fibers. For example, Teijin has a very good dyeability, but not so good a strength. But Yantai has a very you can say moderate dyeability, but very good strength. So it's just the difference between the amorphous and the crystalline thing. And every time when you get a fiber, it is better to take a sample and dye it and see its dye pickup. Because from batch to batch also there may be a variation, because when these fibers are manufactured, there may be a variation in the process parameters. So that will affect your dyeability. That is why we say the incoming inspection and incoming testing is as important as the outgoing inspection and testing.
And just to add this, sir, even from my experience, to give you, like sir was saying, Metara made from Tore. The way they manufacture, they are doing dry spinning. So cross section of their fiber is slightly different than your other fiber. So it's all about trying first 5 kg, 10 kg, and understanding who is the supplier, what technology they are trying to use, and try to get as much as information, because it's not easy to get these details, because that is going to make your life very easy, especially when you are doing dyeing finishing of these materials. Any more question? We can move on to next session. One last question, sir, from my side. I can see many small companies, they want to get into this, and they struggle on the dyeing finishing, whether it's the FR treatment, whether it's the dyeing finishing. So how we can support them, sir? How they can reach you, or how we can help them? Can we give them services of 5 kg, 10 kg dyeing finishing trial, some hand holding for initial, that will be great, if we can support them.
Yeah, the first thing is that the machinery has to be in its place, and once a assessment regarding the available machinery at a place is made, then it can be found out whether these fibers or these fabrics can be made, and can be made at that particular place. And yes, if there is any help that is needed, then of course they can straight away drop a mail to the institute, and then
we will share sir email ID and contact number. We'll set email. We'll share the so please feel free to contact him directly, or through us. Anything is fine.
Anti-static fiber, core yarn or surface yarn is good to pass 1-1. Core.
Yeah, I mean
core is definitely better, since it has a better initially both of them may be having the same level of performance, but over a period of time core yarn performs better.
Sorry. Yeah, it will depend on percentage also. It will depend on your grid spacing also. We are seeing a lot of samples in India where people are just using anti-static in a one direction. They are not forming a grid. I can see anti-static just in the warp direction. There's nothing on weft. So, and these are all 15 centimeter apart. So it looks fine. It will pass your surface resistance test, but the moment you will go for charge decay 1149 part 3, it will have a problem. So you are making a product which will have problem after 6 months or 12 months or 18 months. So better to solve the problem now, and so that you have no problem even after 12 months or 24 months of launching your product.
And plus you need to really factor in the cost factor also, because coarse spun yarns and surface application yarns, they may be slightly different in cost. So it actually you need to take into account the performance required, the cost factor, and then you need to decide whether you need to use the coarse spun yarn or whether to the surface induced yarn.
Or even if stainless steel is doing the job,
Yes.
then why to use, you can use stainless steel based fibers. So I think with this, we can continue our discussion later on. Let's move on to the Shubham. Over to you, Shubham. Yeah.
So,
Thank you, sir. Thank you.
Next question is, thank you, sir, for your insightful session. And our next question is on the requirement of defense forces of inherent flame retardant fibers. This session will be taken by Dr. Manoma Dhalpati ma'am. She has completed her master's in chemistry from BHU Varanasi and earned her PhD in applied chemistry from DTU Delhi. She has been associated with DRDO since 2004 and is currently serving as scientist E in the field of in the protective clothing and materials group CFIS, DRDO Delhi. Dr. Tripathi ma'am has contributed to various research domains, including ferromagnetic fluids, self-healing polymers, polyurea coating for blast mitigation, and more. She has published 15 research articles and has been awarded 2 patents. Her current focus lies in the indigenous development of inherently flame retardant fabrics, fire protective gloves, polyurea coating for self-sealing application, and aqueous clay mineral dispersion for mitigating lithium-ion battery fires. Now, ma'am, I request you to please share your presentation and start the session.
Is my presentation visible there?
Yes, ma'am.
Okay, right. Good afternoon, everyone. I'm Manorama Tripathi. Thank you, Subham, for my nice introduction. Basically, what topic I was given was understanding the requirement of defense forces for IFRs. So it take some time for framing my presentation for this topic. I have frame out something for that. I hope it will be beneficial for you. So now coming to overview. It's not moving. It's not moving actually. Give me some few moments.
You can try again,
Is it visible?
Yes, ma'am. Yes, ma'am, it's visible, yeah.
Okay. The overview of my presentation is first I will talk about some fire hazards and defense, what type of fire hazards are there. And then I have listed some reports and some incidences where which necessitate the need of protection against fire. Then I will list out some inherently fire retardant fibers requirement in defense. Then finally, what we are doing at CFIS, I will give a brief introduction of that, and then I will summarize my presentation. So in land scenario, where the combat scenario, what are the fire hazards? Fire hazards are basically because of explosion in fuel, hydraulic fluids, or munitions. But in the case of terrorist attacks, there are some improvised explosive devices are also there which causes fire. In case of aircraft fire hazards, the aircraft may catch fire in flight or during the takeoff or landing while it is being refueled, or post-crash fires are there. These type of hazards are there, and aircraft fire are more fiercer than land fires. And in the submarine environment, the fire is more dangerous because of the confinement in the structure. So once the fire breaks out in submarine, toxic fumes and smokes may result in fatalities due to inhalation of toxic gases and smoke. And this hazard is aggravated by the clothing or textile if they are flammable there. So NATO ACCP has classified these fire hazards based on the heat flux rates from different sources. And they have concluded that majority of the battlefield fire hazards are of 1 to 200 kilowatt per meter square of heat flux. So while designing the fire protective gears, we have to keep these type of heat fluxes into the mind. So major high risk areas are basically hand, forearm, neck, head and torso area. So we have to protect these areas from fire hazards. Or main factors that influence the burn injury is the intensity of the heat flux. More the heat flux, more will be the burn injury. And duration of the exposure to that heat flux, more the duration, the burn injury will be more severe. And the level and effectiveness of insulation between heat source and the skin. More the insulation and less will be the burn injury to the soldier. And the extent of degradation of garment material during exposure. When the heat, the garment is exposed to heat, it will degrade and give some degradation product which is toxic. So we have to keep in mind while selecting the required material for designing the protective gear. Then condensation on the skin of any vapor or pyrolysis product of released as the temperature of the fabric rises, we have to keep in mind that also. One incident was reported on 18 June 1984, a fire break out in Russian submarine K-131, which causes fire in clothing of one of the members which was working on the electrical equipment. And this fire spread on the adjacent compartment, and this caused death of 13 members of the crew. So while we're designing the protective clothing, it should be fire resistant. Now, in the Second World War, it was reported that the burn injury accounted for about 25% of crew casualties. So we have to design protective gears, that includes helmet, gloves, suit, and boot. That should be designed for very effective thermal protection. And then we have to also consider the function and comfort of the soldier. So a major challenge while designing the protective gear is balance between comfort, durability, and burn protection. So as we all know that inherently fire retardant fibers are basically, they are low flammable, and they derive these characteristics from fiber itself or intrinsic property of the polymer from which the fiber is made. The inherently fire retardant fibers can be made by incorporating additives to the polymer when we are spinning it, and also can be done by the chemical modification of the polymer during polymerization, and then it is spun to the fiber. So before early Second World War, the fire protective clothing which were used was made up of flame retardant fibers, which are flame retardant because of the surface finish or some treatment that were not durable, only temporary. Synthetic flame resistant fibers were developed during 1950s, and then high performance flame retardant fabric come into the picture in 1960s. I have listed here some fire retardant fabrics which are being used in the defense. Some of them are aramid fibers, PVI fibers, fiberglass, carbon fibers, and polyesters. That is flame retardant polyesters. But this list is not exhaustive. These are only few. There are key requirements of the IFRs that they should be self-extinguishing and should have high thermal stability. Then they should be durable. Durable means after certain washes, the flame retardant properties should be effective. And there are standards which specify how many cycles it should be washed, and then the file properties should be determined. There are standards, and they should pass that standards requirement to qualify for protective clothing applications. Then it should be comfortable to persons which are wearing. It should be flexible, breathable, and simultaneously it should give the protection also. It should be lightweight. And one thing I have not listed here is cost effectiveness and commercial availability of that fiber. There are certain non-clothing applications also where the IFRs is used for making tent shelters, sleeping systems, and jeep side curtains of the military vehicles. So now coming to what we are doing at CFIS in this area. Basically, I am coming from Protective Clothing and Material Group, headed by Dr. Prasoon Kumar Roy, Scientist G. And our group charter is to develop fire protective clothing for our defense fire services. And we have developed certain protective clothing for different fire scenarios. First scenario is structural firefighting, where the fire is broke into some structure and we have to go to rescue the firemen, go to rescue the some person, and so they wear this type of clothing, and we have developed a lightweight structural firefighting suit as per EN 469, and it meets the thermal protection and waterproofness of NFPA 1971 also. Some of the layer has been indigenously developed, but there are much of work is remaining. So I want to industry to collaborate in this area to indigenize these fibers, IFRs, so that India can become self-reliant. And so for this suit, technology has been transferred to 2 firms, and suit is now available on the e-portal of government, and performance is better than the minimum requirement. This suit is made up of this is Nomex outer layer, and here the one new material, that AB type PBI is used, fabric is used for the outer layer of this suit. So basically, structural firefighting suit is consists of 4 layers. Outer layer is 12 woven meta-aramid, para-aramid, and carbon. Moisture barrier is EPTFE, PUM meta-aramid non-woven. Thermal layer is meta-aramid non-woven, and inner layer is FR viscose and meta-aramid fabric. These are the requirements of EN 469, which a fabric should meet to be used in fire protective gears. So flame resistant, there is no specimen shall give flaming either top on either side edges. No specimen shall give hole formation in any layer, and no specimen shall give flaming or molten debris. Mean value of after flame should be less than 2 seconds, and mean value of afterglow time should be 2 seconds. So these are the performance criteria. I would not go into much details. Now coming to another kind of protective clothing which we are developing. This is proximity suit. Proximity, this suit is required where there is high radiant component in the heat. So this suit is used, and this is also a multi-layer suit. And here the outermost layer is aluminized layer which reflects the radiant component of the heat, and it protects against the cut and abrasion. Then there is a thermal insulation layer which protects against heat, and there is a vapor barrier which is impermeable to liquid, and then inner layer is a comfortable layer. These are the standard requirement of the fire proximity suit with respect to outermost layer. This is done for outermost layer, that is reflective layer. And then we have developed gloves with high fire, cut and abrasion resistance for rapid action forces. And this work has been done with collaboration with HPT. And here there is core spun yarn having steel as a core and black pararamid as a sheath material. And this glove passes the performance requirement as per 7971-7. And this gloves has been given for user trial to RAF. So there is also this type of application, core spun yarn is needed in the defense. So what is the national status of as of now for IFRs? All the fibers used as a constituent layers are basically being imported, and CFIS is doing much for indigenization of these layers, and in turn for IFRs. So outer layer, we have done some work with ABPBI fibers on batch scale in collaboration with Garda Chemicals and Reliance. And I have shown in the earlier slide that one suit has been made, fabricated with this ABPBI fabric outer layer. And then we are doing some work with Birla for indigenization of FR viscose blend fabrics. Moisture barrier, we have developed a moisture barrier layer meeting the international standards with in collaboration with Wellspun. And now we are working towards developing a non-woven fire resistant fabric based on OPAN for possible inclusion in fire protective gears as a thermal layer. We are collaborating for this with NL Bangalore and Reliance. Other IFRs which we are trying to make is melt spun PI, PK and blend fibers for possible inclusion in fire protective suit and aerospace application with IIT Delhi. Now I will discuss about some results which we have got with AB type polybenzimidazole. That is, it has got a unique combination of high LOI, moisture regain, and tenacity at lower weight. LOI is of the order of 72. This is the outer layer. The steps involved from fiber to fabric conversion. This is the staple crimped fiber, then sliver. All you must be knowing this So this is the degradation behavior of ABPBI around 1000 degree. It has got 30% ash content, which is responsible for its better performance in fire. When we expose to fire, a flame, it is we have compared basically ABPBI with aramid, and we have seen that in the case of exposure to flame, ABPBI don't shrink much as compared to aramid. And when it was exposed, you can see the exposed area. It is not much shrink. But in case of meta-aramid, there is a phenomena called break open. मतलब यहाँ से that fabric is removed, a piece of fabric that is very critical. This is the same images of ABPBI. As we can see that there is integrity is maintained after exposure also. While in case of aramid, the integrity has gone. The fiber integrity has gone after the exposure. When we compared the second degree burn time, the ABPBI outperformed as compared to aramid. And then coming to the moisture cum thermal barrier layer. Here the moisture barrier is composed of microporous EPTFE layer that prevents due to its hydrophobic nature, it prevents ingress of liquid water or chemicals. And then there is non-porous hydrophilic PU layer, and it is in between this microporous PEPTFE and non-woven fabric, that is thermal barrier, and this is used for as a moisture barrier layer. This is the step involved in the development of indigenously moisture barrier layer. In this, hydrophilic polyurethane resin is prepared, and FR additives and wetting agent had been added to this. And then this prepared PU resin was coated on silicone release paper, and then PU coated on silicone release paper was transferred to EPTFE membrane by transfer coating, and then PU coated EPTFE membrane laminated to base fabric, hot melt breathable PUFR adhesive with the help of hot melt breathable PUFR adhesive. And then the moisture barrier layer was made, and this was evaluated for its properties. This is done with a company called RC Chemicals in Pune. And when we compare the CFE's developed moisture barrier with the Poral that is commercially available layer, the CFE's developed layer also passed the criteria mentioned in EN 469. So lamination of this PU EPTFE has been done with some non-woven thermal barrier layer and to make moisture cum thermal layer. Now coming to the thermal barrier layer, what we are doing in this thing, we are collaborating with NAL. NAL basically developed a process for preparation of carbon fibers. The process involves oxidation of PAN to prepare open fibers, which were subsequently pyrolyzed to obtain carbon fiber. But we are more interested into open fibers for making the thermal barrier. Because the limiting oxygen index of OPAN is 45 to 55%, and their flame and heat and flame dimension stability is quite good. Easy possibility into yarns, woven, knit, and non-woven, and they are soft, comfortable felt and fabrics. Electrically non-conducting, excellent thermal chemical properties. Low toxic gas emission upon flame exposure. But there is an issue. Commercially available of industrial grade PAN fibers are very difficult to find. There are industries which are making PAN fibers, but the industrial grade PAN fibers are difficult to find. This we have done the TPP testing for this oxidized PAN, and we got that it is quite high stole curve where it cut the stole curve. That time is quite high. Matlab TPP rating is quite high for open based. So now to summarize, the requirement for IFRs in defense are crucial to ensure the safety of military persons, and these fibers should balance high performance protection with comfort, durability, and cost effectiveness. R&D in the area of fiber development, processing of fibers, fabrics, and testing equipment needs to be done. And most importantly, commercial availability of them should be ensured to make India self-reliant. Thank you. This is our team. Thank you so much.
Thank you, ma'am. If there's any question, please feel free to ask. We'll take one or two questions.
Sir, my name is Manish Chabra. Ma'am, my name is Manish Chabra. Thank you. That was a good presentation. I just wish to see the slide on moisture layer once again, wherein you've shown the steps involved in that.
Okay. You can write to me and we will share whatever information you will need.
Okay. I just wanted that particular slide. That's okay. I can see later. Thank you.
What I will do, I will share details with with everyone, ma'am's details and email ID, so you can feel free to contact her directly.
Actually, as a company, I'm trying to put up another hot melt PUR facility. So I'm just trying to analyze, what are the things, because that is one layer where that comes handy. So
actually, I'm not working on that area. My team member is working on this area, so I can direct you to him or her. Who can.
Thank you.
Take one more question. Are there any applications that use an aramid layer as an outer layer?
Sorry, sir.
Take one more question. We want to know if there is any layer where we are using aramid as an outer layer. I think your firefighter suit is having aramid as an outer layer.
Outer layer is meta-aramid, para-aramid, and carbon, that layer. But we are also interested in ABPBI type of layer, but ABPBI is not commercially available right now. So we want that this ABPBI is quite good material. If that can be replaced, and Indian also. So if that can be replaced, that can replace meta-aramid. Very happy.
So Kanan, please ask your question.
Hello. Hi, ma'am.
Please go ahead.
Yes, sir. Actually, that EN 469, if you do that test for that mannequin test, the time should be, I think, 5 to 6 seconds only. But madam mentioned that they want 150 heat flux at the timing of 10 to 12 seconds for the burning the fuel, 7 to 12 seconds. So I have doubt whether that EN 469 will meet that burning fuel requirement by DRDO.
What heat fluxes I have mentioned there, the fuel source and then heat fluxes, because there is no standard for above 84 kilowatt per meter square.
Okay, because so maximum is 84.
Yes, there is no standard 1971 NFPA also mentioned 84 kilowatt, more than 84 kilowatt, it doesn't mention. Actually, we are targeting for to develop protective gears for higher heat fluxes. But till now, it is 84 kilowatt per meter square.
Yes, madam. 84, and the time is for I think 5 to 6 seconds.
Yes, yes, yes.
But your need is 7 to 12 seconds.
No, that was not our need, but we are targeting higher heat fluxes, but standard is not there. Any standard,
Okay.
any worldwide, any standard is not there.
Okay, understand, ma'am. Thank you very much.
Any other question? Okay, ma'am, thank you very much.
Thank you.
Now I request Dr. Nanda sir to summarize all the session.
I need 10 minutes to complete my presentation. My presentation is still pending, so I'll just need 10 minutes to conclude my session, and then we can have final round of questions, and we can conclude this one. So just give me 1 second. I'll just share my presentation. So Shubham, I'm logging in from presenter mode, right?
Right. So share all windows.
Sorry?
Share all windows. In time. In time.
We have cover. Thank you. Yeah. So yes, so far in morning we covered a variety of inherent FR materials and how these can be blended with conventional fibers or even with FR treated. Now we are going to talk a little bit about ultra high molecular weight polyethylene, which I believe may become next polyester in future, because I can see price dropping down from $25 to now $8, and it's amazing material, and hopefully we'll have one Indian manufacturer also coming up with a plant in a year or two. So this is a fantastic material, ultra high molecular weight polyethylene, and when I started using this in 2012 or 13, we used to get 37, 38 gram per denier. But now we are seeing ultra high molecular weight polyethylene, which goes even up to 15 gram per denier, 17 gram per denier. So, I can tell you now there are maybe 20 types of ultra high molecular weight polyethylene. So it's very important to validate your material. And like I said, it's fantastic because, first of all, it floats in water. It's very lightweight. And a lot of things can be done with fiber. We are processing staple fibers. We are blending staple HPP with cotton. We are processing 100 denier, 200 denier, 300 denier. So you can see a range of ultra high molecular weight polyethylene fibers available in market now. We are even working with black color, dope dyed. Abrasion resistance is very high. One of the major challenge with this fiber is melting point. So at 100, 120, it starts degrading. For that reason, we really need to be very careful which product and which end customer we are targeting with this material. One of the development we are doing using core spinning technique, where we are putting HPP fibers or ultra high molecular weight fibers in core and aramid on sheet, so that the exposure to fire comes to aramid first and HPP is hidden inside to provide the high strength properties. New generation of materials are already in the market. There are maybe 4 or 5 big manufacturers of ultra high molecular weight polyethylene, where they have started putting up very hard particles at the time of extrusion, and these particles are glass materials, silica carbide, or tungsten powders, you name it, and there are many patents coming up. And the idea is very simple. in order to improve, especially cut properties, the idea is not to use any steel or glass. The idea is these hard particles which are reinforced in the material can take care of that. So these are known as a reinforced HPP, and I can see huge requirement coming up where these materials are going to be used, and standard HPP may take a back seat, but that means we should be ready with knowledge on how to use these materials because it's not easy to process these on your spinning machine or knitting machine. There's a lot of wear and tear of machines when you are using these hard materials, and so it's about looking into the opportunities. Bikers denim, we are doing a lot of projects where we are trying to develop cotton and HPP blended bikers denim, black color and blue color. Again, the idea is to improve abrasion as well as cut performance for our normal denim. There are few inorganic fibers which are also being used in protective textiles. Basalt and glass is the most common one. Like I said, glass 5.5 to 9 micron filaments are used for protective textiles. Above this, mostly used for insulation or for automotive applications. So we are working with 50 denier, 100 denier, 200 denier, and I can see a lot of opportunities. If PBFE coating can be done on glass, or if PVA coating can be done on glass and can be used in protective textiles, very interesting product, especially because the price is interesting. So for a manufacturer, this is a very interesting product if we can use this glass for protective textiles. And basalt is also natural fiber, and this is also, I've seen many applications where 100 denier and 200 denier of basalt is being used in combination with aramid or HPP to develop a few products. Few slides on the insulation side, how inorganic fibers are playing a good role in building insulation, automotive insulation, and how I can see a lot of opportunities in this area, both for researcher as well as business owners. Just to give you idea, variety of products are available in market which uses e-glass, whether it's a needle punch or glass roving or woven glass. But the moment you start doing tests at 700 degree and 800 degree centigrade, you understand that there are different types of glass available, and there are requirements where we have to do this testing at very high temperature. So this is just example of testing performed overseas where e-glass starts shrinking at 800 degree centigrade, whether you have another variety of ECR glass which is doing well. But like I said, we need to do our own R&D on different types of glass. And 14 micron glass is manufactured in India, but less than 14 micron is still being imported. And we are trying to work with a few glass companies, and we are trying to request them if they can do some R&D on 10 micron or 12 micron, So I can see some good work coming up in next 1-2 years where we can start producing at least 9 micron glass for our own consumption. Alumina fiber, this is a very interesting material, polycrystalline fiber. Very less is published, and these are still being very much protected fibers. And a type of this, I will say, asbestos, which is banned now because of these are respirable fibers. But then you have polycrystalline fibers, which has better chemistry and better dimensions, higher micron level, which are not respirable and which are not banned. And these fibers are being used for some very interesting insulation applications. And we are trying to do some work on this fiber. And again, I can see huge demand for these fibers coming up because they can do some work which glass-based insulations cannot do. And like I said, it's a very interesting material to look into. This can go up to 1600 degrees centigrade, and we have samples and we have performed some tests, and it's quite interesting. And polycrystalline fibers is again we should be looking at. Metallic fibers, it's very interesting. Like I said, in India, we have 30 micron, even up to 20 micron of stainless steel wires are available, but less than 20 micron when we talk about 10 or fiber form, 8 micron or 7 micron, that becomes challenging. And that's where it becomes interesting for protective textiles. If we can incorporate a percentage of these fibers with polyester or polypropylene or cotton, we are seeing some interesting results. Especially we are doing a work with National Physical Laboratory where we have even filed a patent on trying to develop some polyester-based sensors out of the stainless steel and blended material. Tungsten has got very good future. It's very dense material, and good that now it's available in India. We have Indian manufacturer who can make these tungsten wire, and I can see many smart textiles coming up with these materials blended with both high performance as well as standard materials. So these are the areas research enthusiasts should look into. There are other fibers. Definitely, maybe March or April, we'll conduct another session where we'll try to cover other fibers such as PEEK, polyphenol sulfide, PTFE, because we have ordered 100 kg of each of these materials. By March or April, the next session, definitely, we'll cover these materials. And last two slides, just opportunities for like ma'am was saying, Manoma ma'am was saying that we have these technical fibers already available in India. The proof of concept has been done, but now we have to take it to the next step. We need to go for 500 kg, 1 ton, 2 ton manufacturing so that we can do bulk scale trials. Dapar viscose, metaramide, ABPBI, OPAN, all these fibers, proof of concept is already done, and few of them are in the next stage. So yes, excellent opportunity. Dyeing finishing of these materials is still a challenge. Very few are very clear about how this can be done correctly. Like sir mentioned, you have to do it first time correctly, because a repeat will be a disaster. It's not like polyester or cotton. You done mistake and you repeat it. Here, if you do re-dyeing, you will find some surprises, and that becomes an issue. Crimping cutting is an interesting area for research as well as for business opportunities. Stainless steel fiber, like I gave example, 20 micron available in India at $35, and 8 micron is being imported back at $80 to $85. So our material is going out and coming back in a much finer version. So something we need to do here immediately, because our raw material is there and just we have to work on the technology. Recycling, I think it's the best opportunity for 2025. All these high performance fibers, we are based in Panipat, which is a recycling hub of India. Already a lot of recycling is being done in Panipat, but we need to do a lot of research on how to recycle these high performance fibers, how we can do cutting, crimping, removal of finishes, how we can reuse it, because most of these materials are right now going into landfill. Whether it's gloves, whether it's ballistic jackets, most of these are going into landfill, and there is a good opportunity if we can study and we can develop how we can recycle these materials back to some application. So with this, I would like to conclude my session saying that high performance fibers, we really need to play with these materials. If you are a small company or big company, we need to allocate certain funds where you buy 50 kg, 100 kg of these materials, start playing with that, try to understand that. Standards, very important. Before you start manufacturing, you need to understand which standard you are going to pass, because you can keep on doing a lot of R&D, but we need to understand what is your standard, what is your requirement. Based on that, we have to select material and we should be developing it. Collaboration is the way forward. Industry cannot do alone. Academia also, they are doing fantastic job, but we need to make sure that we are working together. I'll say NTTM is an excellent initiative. We really need more and more initiatives like this. And yes, awareness is needed. We are trying from our side and we need more and more partners to share some of the knowledge which are in the open domain. And our post-lunch session is fully focused on testing validation, that is only on the offline mode, not on online mode. So with this, I'd like to conclude my session. You can see these are our academic partners, and I really suggest that we should be working together, and we should try to understand, how we can, share this knowledge. With this, I'd like to thank you. And if there's any question, we can take a few questions.
So one question is in chat box.
Sorry, wait, I think I've got disconnected or not. Yeah. I can see a question. What additional feature would be required to spin high performance fibers in existing melt spinning machines? My suggestion is, or what I feel is the attitude, first of all, attitude, because the first requirement is your thought process. I'll give you experience. I'll give you my experience. When we started setting up one blow room, one carding, I was told that no, it's not possible. You cannot run one blow room and one carding, and you cannot process aramids because you need at least two carding machines to balance a blow room line. Okay. Now we have processed over 500 tons of aramid on the same line. So all I'm trying to say that we really need to start somewhere, and need to have partners like Kushinder sir, you need to have Manorama ma'am, you need to have Ghosh sir, who can start chipping in, and suddenly you will see that your traditional machines can do a lot of things. Okay. I can see this question of 1149 part 5 and EN61345051. Sir, we are also doing a study on these two standards. I know one is for ESD for electronics, and other is for protective textiles. But we have found that the basic is same charge decay test. So we have charge decay setup. We are trying to, I think, Shubham, we have got the standard now. We have bought the standard 61340, and I think we can perform both tests, charge decay test on both. But give us a week or 2 weeks, we'll be able to share more details. And if we can do the test, that will be great. We can share the report to you. So thank you so much to everyone, and we'll be sharing a copy of our presentation. And Shubham, you want to add anything?
So before we proceed further, we would like to have open camera of all the participants.
So we just want to take one group photograph if it's possible. That will be good.
Hello. Hello.
Yeah, hello, please go on.
Yeah, this is Satish Aprai, sir.
Hello.
Hello, can you hear me, sir?
Yes, please go ahead.
Yeah, sir. I am working with the institute DKD. So we want to try to process the Kevlar fibers on cotton card. Is it possible?
Yes, we can get you 38 mm Kevlar. We can get you 38 mm para-armored fiber. You can definitely process 38 mm.
So what are the changes we need to do it on machine so that we can process because we have tried it, but there is some limitation while processing. It generates a lot of static.
No, I will help you with all these. You need to optimize the LD40 water composition, the anti-static spray, because it's about avoiding lapping and all these things. So we are just working on preparing standard operating procedure for aramid spinning, and hopefully in another 1 or 2 months we'll be publishing a data for everyone to go through. So my suggestion is drop us email. What I will do, I will share the parameters, and I'm sure 38 mm. You can process it,
48 mm, okay.
38 mm para-armored fibers are available.
Okay.
And you can process 38 mm. You will struggle maybe with 44 or 51 or 48 mm, but 38 mm I'm sure, because I know in UK cotton spinning they process 38 mm. Even in Europe, all cotton spinners they are able to process pyramid and these lines. Even they are blending 10% or 50% of cotton. So all these things are there. So it's about trying it out. Let's try it out again, and we can drop me email separately for this.
Okay, okay. Thank you, sir. I will put a mail separately regarding. I have some difficulty while processing this Kevlar in non-on cards also. So I will put a separate mail for you.
Separate email, because see, there are two things. First of all, the moment you say Kevlar, then we need to take approval or permission from DuPont, because Kevlar brand is owned by them. We are licensed partner of Kevlar also. We are processing Kevlar also. But if you are particular about Kevlar, I'll connect you to DuPont and jointly we can help you. But if you are looking for just Pararamid, again, you have other brands, and I can help you with 38 mm fiber, 510 kg. You can check a trial and let me know exactly what problem you are facing, and we can support you. No problem.
Yes, sir. I will put a mail to you.
Okay.
Okay. Thank you, sir.
Shubham, you want to take photograph and certificate? Yes, no problem. We will issue a certificate. It's not a problem. Thank you, sir. Thank you so much. And my apologies, we are not able to do our post-lunch session online. Next time, definitely we'll try to do our lab demonstration also online, maybe in March, so that we can showcase what we are testing, how we are testing, and maybe we can learn, from some of you. If we are doing something wrong in our lab, so we can learn. That is the idea. So with this, thank you so much. Wish you all Happy New Year.
Thank you, sir. Thank you. Thank you.
Thank you, sir.